Okay. Good morning, ladies and gentlemen. Welcome to the 2021 International Symposium of Precision Environmental Medicine, Emerging Scientific Links Between Air Quality and Health. On behalf of the conference, I'm delighted to welcome you all this online conference. 欢迎各位贵宾莅临2021精准环境医学国际研讨会。空气品质与健康之新兴科技连结，我是施以威德，仅代表大会很高兴欢迎大家参与这次线上会议。In the very beginning, I would like to introduce our distinguished guest online today. And now it's given me great pleasure to present you Professor Chen Baozong, the chairman of our conference, and the director of the National Institute of Environmental Health Science and the National Health Research Institute. Now we are very delighted to the Chairman Dr. Chen to make a statement. 首先，让我们来欢迎介绍今天与会的贵宾演讲者。现在很高兴的向各位介绍我们今天的大会主席陈保忠教授，目前也是国卫院环医所所长与公卫学会理事长。请主席陈保忠所长致辞。
各位线上的与会贵宾，大家早安，大家好。我们就开始今天的2021年精准环境医学研讨会的开会了哈。那我今年的主题当然最主要是围绕空气品质与健康强调它的新兴科学的连结啦。那这次呢，我们这个研讨会呢，也结合了台湾公共卫生协会整个联合年会的活动。那这个是今年公共卫生联合年会，从今天开始起跑，一直到这个礼拜天10月3号。那今年年会的主题是大疫情时代下全球公共卫生的冲击与挑战。那我们这个研讨会的议题空气品质与健康，我想更符合在全球卫生的这个议题。那大家也知道这个空气品质的议题不只是国内的民众关注，那在全球的所有的国家、所有的民众都非常关注的议题。那特别，我想贵宾们大概都知道，我们在去年在上个礼拜9月22号，WHO 也宣布了这个全球的air quality 的 guideline 那在这个 guideline 之下呢，我们还有很大的空间，可以在努力的地方。所以，今天的研讨会呢，我想，我们就邀请到国内外的一些重量级的学者来共同参与。特别是日本的 Sachiko Hojo 教授哈，还有我们在美国的陈荣记陈教授哈，还有事实上我们的团队里面的郭卫良教授也在澳大利亚哈，所以我们希望今天的活动呢，针对这个环境的议题，特别在空气污染上面的怎么样去精进哈，我想不止这个所谓的精准，不只是在环境测量的精准，我们更重要知道致病的机转因果关系甚至是个人的易感性才能有一个精准的政策的介入，精准的个人的措施。所以这些议题的讨论呢，我相信对日后我们的空气品质的改善会有重大的贡献。那最后呢，再一次谢谢所有的演讲者，所有的线上的与会的贵宾在今天的共同的参与。在这全球 COVID-19 疫情之下呢，我想我们更需要 有清新的空气可以呼吸。希望我们共同来努力，最后进驻大会圆满成功。谢谢各位，谢谢。
Thank you, Director Chen. Today, we are very delighted to invite Liang Genyi, the President of the National Health Research Institute, and Yang Junyu, the President of Kaohsiung Medical University, to give us the opening remarks. Welcome to President Liang and President Yang. 今天我们很荣幸能够邀请到国家卫生研究院的梁根义院长与高雄医学大学的大家长杨俊义校长来为我们致辞。现在就让我们用热烈的欢迎，来欢迎国家卫生研究院梁院长的致辞。
杨校长、陈所长以及线上与会的贵宾，大家早安！欢迎各位出席2021年精准环境医学国际研讨会。国家卫生研究院的国家环境医学研究所以实证医学研究为基础，着重预防或减少环境有害物质对国人健康危害及影响，并透过新颖技术提升医学研究品质，希望以环境科学教育概念转译作为政府单位之研究智库。目前针对现今国内外最重要的议题，也就是空气污染，进行防治策略的研究。根据 WHO 全球疾病负担报告，他们推估2017年因为室内室外环境空气污染所造成的死亡人数达到470万人，共造成1亿4700万损失的人年。那死亡呢，以缺血性心脏病、慢性阻塞性肺病疾病、下呼吸道感染为主，其中呢又以亚太地区最为严重。然而，空气污染防治策略需要整合多项跨领域的资讯，包括暴露评估、毒理、流行病学、数据分析、健康风险评估与政策转移等领域的合作，才能够厘清及有效防治空气污染对国人健康的影响，也是现今国内外最困难的环境医学议题。2021年精准环境医学国际研讨会以空气品质与健康之新兴科学联结为研讨的主题。我们邀请了国内外具有声望之学术及跨学科研究学者，提供精辟的研究，包括环境、流行病学、暴露科学、毒理学、系统生物学研究、数据和分析科学、空气品质物联网应用与室内空气致敏性等议题等相关问题与技术，希望能借由此次与国内外不同领域专家学者交流讨论，完整的汇整出合宜可接受的精准环境暴露与健康风险的研究方式或改善措施，来提出控制地区的空气污染与合宜政策，期待朝向空气品质之精准环境医学目标迈进。那最终希望是同时可以推动环境医学的教育、研究与服务，以提出本土环境暴露的健康影响的相关政策，提升国民健康，彼此举行空气品质与健康之国际会议更具有意义。最后预祝精准环境医学国际研讨会顺利成功。提升国民健康，彼此举行空气品质与健康之国际会议更。
Thank you, President Liang, to speak. And we also invited President Yang to give us our opening remarks. Welcome. 现在我们也用热烈欢迎高雄医学大学杨校长来替我们致辞。
国家卫生研究院梁根义院长，国卫院国家环境医学研究所陈宝忠所长，各位与会先进，各位女士、各位先生，大家早安。今天非常荣幸代表高雄医学大学欢迎大家。很可惜，这次因疫情改成线上会议，无法以东道主的身份来招待大家。但是也感谢各位专家学者们愿意以线上莅临指导。 期待跟各位一同关心空气品质与健康之新鲜科学连结之精准环境医学议题。近年来，空气品质与健康防护已经是全球迫切关注的公共卫生与环境医学议题，不仅需解决因空污对各类疾病所造成之负担与影响外，对于国家整体经济之关联性亦不容忽视。而在目前的研究中，流行病学关系之建立、空气品质暴露评估，包含成分组成与来源的鉴定，以及人体间异质性与易感受性都存在相当的不确定性。鉴于此，追求空气品质与风险识别、健康风险评估、风险控制的精确性，一直是这个领域想要努力实现的目标。同时，也希望相关的见解及回馈能提供给政府单位，作为未来公共卫生及环境医学相关领域之政策规划上之具体科学实证与依据。2021年精准环境医学国际研讨会将聚焦于空气品质与健康之新兴科学连结，并邀请国内外具有声望之学术及跨学科研究学者提供精辟的研究分享，包括环境流行病学、暴露科学、毒理学、系统生物学研究、数据和分析科学、空品质联网应用与室内空气致敏性议题等相关问题与技术，内容丰富精彩可期，期待能朝向空气品质之精准环境医学目标迈进，长此以往，吸引更多人才投入这个领域，为国民健康和福祉努力。再次的感谢梁院长、陈所长促成这么好的会议，让有志一同的人得以尽情的交流、交换新知、相互切磋。俗话说，好的开始就是成功的一半，相信这一次会议一定是非常的成功。谢谢大家，也祝大家身体健康，万事如意。
The next agenda is a group photo. And try to open your camera on the web assistant to take a photo. And now we, Professor Hoja and Professor Zhuang, yeah, okay. So 接下来的议程是线上大合照，请线上的师长贵宾们帮忙打开 Webex 上面的镜头，让我们合照留影一下。Okay. So, 何老师也在线上，林老师、郭老师，好，好，然后我们数1、2、3，然后我们就是拍一个大合照这样。OK，1、2、3。Smile。子伟，你那边会帮忙拍吗 ？OK。One more。1、2、3。Okay. Okay. So, thank you for all professor and discussion guest. 谢谢所有的教授和我们的现场的来宾。Okay, ladies and gentlemen, let us announce some important things. Because this conference is online conference, so in the online discussion session, we open the chat room on YouTube to the audience. So please feel free to ask any question or share any thought with our speaker. We hope everyone who enjoying this wonderful presentation. 所以在大会这部分有一个重要的事情，先跟大家宣布。我们在 YouTube 上面会向观众开放一个聊天室啊，如果任何有意见对任何建议或任何想法请在 那个 YouTube 上面的聊天室可以提出我们会请工作人员交由主持人统一提问。Okay, so let's take a short break right now. The next session will start in 20 minutes. Thank you. 所以我们接下来要请各位贵宾跟各位的听众稍微休息一下。我们下一个议程将于20分钟后开始就9点50分的时候开始谢谢大家。 Thank you all for your patience. And now for the first keynote speech, speaker is Professor Chen Longji. We are honored to have Professor Wu Mingchang of Kaohsiung Medical University and Professor Lin Pingping of National Health Research Institute serve as our moderator. Now, let's welcome Professor Wu and Professor Lin. 本大会第一次场次演讲，讲者为陈龙纪教授。我们很荣幸邀请到高雄医学大学公共卫生学系以及环境医学研究中心主任吴明昌医师和国家卫生研究院环境医学研究所林平平研究员担任主持人。现在让我们欢迎吴医师和林研究员。
Good morning, everyone. Welcome to the first section of 2021 International Symposium of Precision Environmental Medicine. Dr. Lin and I, we co-chair this this first session. And I'm Mingchang Wu from Kaohsiung Medical University, and Dr. Pingping Lin from the NHRI. First, I'm going to introduce our keynote speaker, Dr. Longji Chen. Dr. Chen graduated from National Taiwan University in 1976. Later, he went to the USA to pursue his graduate degree, and later he received a master and a PhD degree from the New York University, major in environmental medicine. And after his graduate, he went to the MIT to become the research scientist. In 1994, he came back to the NYU School of Medicine to become the assistant professor at the Department of Environmental Medicine. And right now, he is a full professor in the same department. And Dr. Chen is an international recognized expert on inhalation toxicology. And he has extensive experience to study cardiopulmonary effect related to inhaled pollutant. He also served quite a number of international committee and the study section in his expertise. And right now, Dr. Chen is already publishing more than 200 research paper and book charter. So he is quite experienced on the air pollution, inhalation toxicology, and also the adverse effect of cardiopulmonary disease. So right now, he is going to talk about the toxicology study of health effect of a particular metal component. Let's welcome Dr. Chen. Dr. Chen, please.
Yes, thank you very much for the introduction. And I'm honored to be invited to this meeting. And especially, I'm the 我是公卫第一届毕业生，所以感觉更荣幸能够跟公共卫生学院一起有同样的会议。Okay, today we're going to talk about the toxicology study of the particulate matter components, and this is based on several years ago we completed a more comprehensive study, and I'm going to present some of the data of animal research, chronic exposure to concentrated ambient particle, as well as in vivo and in vitro short-term exposures. And toward the end, I'm going to introduce some more recent health concern about wood fire in California. And it's kind of a special event that PM component actually is a very important factor in terms of their risk assessment. So okay, this is my collaborator, both in NYU and at another university. And you can see later that this research involved 4 different other institutes other than NYU. And these are my collaborator in those institutions. And today we're focusing on particle. This is a particulate matter present in the ambient air pollution, and have the variety of different sizes. And most important component of these particular fraction is the smaller than 10 micrometer, as well as smaller than 2.5 micrometer. We call it PM10 and PM2.5. The research on particle pollution started in 1952. I think a lot of you are probably familiar with this episode. And during that 1 week period, there's a tremendous amount of air pollution that you can see that even during the daytime, you need a person to the bus to guide the bus around the city. Otherwise, the driver cannot see anybody. So the concentration of PM at that time is enormous. And so you can see that changes in concentration is corresponding to rises in mortality. Number of people die during that period. It's about 4,000 to 6,000, and it did not go down to the baseline level even 1 week later, and it lingered around for several more months. My colleague Casito and George Thurston, during that time, the only parameter they monitored in the London episode is SO2 and SO2 and British smoke. And you can see that British smoke is equivalent to about 4.46 milligram per cubic meter. We never see this type of concentration that much in the modern days. And Casito and George Thurston reconstruct that based on these 2 parameters. They estimate the possible concentration of sulfuric acid during that episode. And they do the correlation. You can see that the sulfuric acid actually correlated better than the British smoke or sulfur dioxide by itself. So this is the first indication that perhaps the component other than what you are measuring is actually contributing to the health effect of London smoke. And modern days, right now, the concentration is much, much lower because all the government implement the PM reduction technology. And however, if you compare the 2 studies, one conducted in between 1982, using the population of 1982 to 1998, the ACS cohort versus the AARP cohort, that is between 2000 and 2009, there is about 30% reduction in there's a 30% reduction in PM concentration, but there is no corresponding reduction in mortality, which means that what we can do to reduce all the government measure to reduce the air pollution is removing those components that are not really that much very toxic. So all the toxicity remain, even though with a 30% reduction in PM. So we need to find out, even at this low concentration, what is the component that are responsible for the adverse effect that we are seeing in the PM pollution episode. PM are entering the body mainly through the lung, but they can also enter through the blood. They penetrate it from the lung epithelium into the bloodstream, or go through the nasal cavity and olfactory bulb to get into the central nervous system. And then once they get into the body, the systemic oxidative stress inflammation is responsible for most of the cellular response in each of the organ system, and that produce adverse effect, eventually leading to mortality. And you can see that there's a variety of organ system is affected. And as a matter of fact, that whichever organ that we look at, we will always see some changes in mortality, changes in the organ system. And this is a molecular pathway that are responsible for the cellular change and organ system change in the body. To me, this is it's not as important as if we can stop the pollution to enter in the body to prevent this from happening. And once the particle get into the body, not much you can do to reduce the toxicity. So what my interest is to find out what is the pollution before you enter in the body, what kind of it, what is the source category that can respond for the change. And once we know that, we can use the pollution policy to reduce the exposure and at the same time reduce the impact of PM exposure. Okay, so this is a typical pollution from the automobile emission, from power plant, from factory, from secondary aerosol, secondary formation. It can produce toxic component. And so if we can figure out which one is responsible, and we can have more effective control measures. And back in early 2010 or so, NYU has a very comprehensive study to look at the association between the PM chemical component that are responsible for the changes in human and in laboratory animals. And that study is called National Particle Component Toxicity Studies, briefly called NPAC study. This is funded by Health Research Institute, and in that study we have four components, and each one George Thurston and Casito is responsible for human study. They're looking at the chronic exposure and acute hospital admissions. And Terry Gordon and I are responsible for the animal study and in vitro studies. And in the US, because this is a big country, the source of PM have very unique distributions. And in terms of traffic, is over the place because it's a car-oriented society. So you can see that traffic is over the place. But for oil combustion, you can only limit it. The largest contribution of contribution of oil combustion PM is mostly located in the northeast of New U.S. Along with some of the large seaports. And for the biomass burning, it's almost evenly distributed. But during the winter, most of the northwest are using the biomass burning as a fuel source. And for coal combustion, and most of the power plants are located in the Midwest because the location of the fuel source. So the west-east of the northeast region of the U.S. has dominated by coal combustion emissions. So we choose 5 locations to do our study, and we simultaneously did an exposure in Manhattan and in Tuxedo, New York. It represents the urban and rural exposure. And we go to East Lansing to look at near the Ohio Valley, to look at the coal combustion, and also industrial, because there's a lot of steel mill around the area. And in the winter, we went to Seattle, Washington to look at the contribution from wood smoke, and in Irvine, California, and we're looking at the contribution from traffic. And we did the concentrated ambient particle concentrated system called CAP system. We concentrate the ambient particle 10 times, and we do exposure for 6 hours a day, 5 days a week for 6 months, and 5 different locations. And we did continuous heart rate and heart rate variability monitoring using telemetry. And we also are using ultrasound measurement every 2 months, and eventually sacrifice the animal doing the histology to look at the long-term effect on atherosclerosis. And this is the system we use, and it's fairly compact. And I'm not going to get into the detail of this system, but it's a small system, about 3 feet by 5 feet around, and we can move around the system to different locations, different universities. And so we eliminate some of the variable associated with the exposures, because the same system is used for most of the exposure, for all the exposure and different locations. And this is we did a pretty good job of concentrating the ambient particle between 6 to 10 times, and by different locations. The ambient level varies, so it's the CAP concentration, and both the black carbon and organic carbon also vary between these locations. So we take advantage of the changes, the differences between different locations, so we can figure out what is the component using source apportionment analysis to figure out what is the component they are responsible for the change that we see at each of these locations. And we did the continuous monitoring for heart rate and heart rate variability. And you can see that it varies between time of day, between different locations, urban and rural, different time of day, even different day of exposure. So this change actually is tracking very well with the PM composition change. We took a daily sample at each location each day, and we use the XRF to look at the concentration of each element, 37 elements, and we do the source apportionment analysis and figure out what is the source contributed to the change in the heart rate and heart rate variability. And the number of significant change from this cardiac function, and is related to the adverse effect. And we're looking at how many number of change on these parameters, and sum it up. The larger the number you see, the greater the health effect on the cardiovascular system there is. So right away you can see that New York City has many more different sources, and then the Sterling Forest, the rural area, and they have greatest change to the cardiovascular system. Residual oil is one of the major fuel source to heating of New York City area, and has greatest change. And traffic is also part of the source that contributed to that. Some of the industry is still around at that time, and sulfur coal combustion also related to the change. We can also pick up fireworks. The July 4th Macy usually have a firework, and we can actually pick up the health effect associated with firework. Firework contain a lot of metals, and we actually can see the contribution from that. And Sterling Forest, the New York rural area, naturally has a less PM concentration, similar concentration, but they don't have a lot of primary emissions. They have a lot of secondary emissions, secondary aerosols, and we can pick up coal combustion and nickel refinery from this source. And Seattle and the Irvine LA area is mostly related to the traffic, and the soil can come up to be the first component to be seen, but soil is not really directly. It's really a resuspension of the soil by traffic. So the soil component actually is a part of the traffic dust related to that. And in Seattle, during the winter, we actually pick up wood as one of the contributing factor. In East Lansing, coal is one of the important factor, and some of the industry also contributed to that. And you can see the soil is from all the site that we see. This is because New York, U.S. is a car-dominated society, and resuspension of soil from traffic is becoming one of the major sources of for the PM that contribute to the adverse effect. And we use the ultrasound and in-fast atherosclerosis area, as well as the cross-section of the aorta, to look at the chronic atherosclerosis resulted from PM exposure. And very interesting is that we only see changes in the East Coast, okay, from the area of New York City and also East Lansing, because the area are impacted more by conditions. In the West Coast, we did not see any change in atherosclerosis because the coal combustion, they don't use the coal combustion as their power source. So the pollution is not there, and the chronic effect that we see with the PM exposure are related to mainly related to the changes in from the coal combustion pollutions. So this is just some short conclusion. The heart rate variability are associated with changes in the PM exposure. The rate of change is vary with different site and different time point. It's mainly related to several important source category. For the long-term plaque progressions, coal combustion is one of the major reason for the adverse effect. And for our in vitro study, and also called oral pharyngeal aspiration study, we collected particles from locations that we conducted chronic animal exposure. And we use a system called CanVolt to collect the coarse, fine, and ultrafine particle, and we extract that and expose to the lung epithelial cell or pulmonary endothelial cell, as well as the cardiomyocyte. And we use the viability and reactive oxygen species production, fluorescent from the dichlorofluorescent compound, and we also look at the cytokine productions. For the oral pharyngeal aspirations, we look at the lung lavage endpoint and how many neutrophil is present, and also cytokine concentrations. And so we look at the contribution from 5 different locations, the site, and we look at 3 different sizes, and we look at 2 different seasons, winter and summer. And you can see that everything is important. So location make a difference because different locations have different compounds, and size is different because size is related to how the aerosol is generated. Season also affecting the aerosol's fate in the atmosphere, as well as the source, or what source is being produced. And there is an interaction between the site and size, and size and season, but there's no interaction between site and season. So everything is important. So if you want to look at that, what is the component they are related to the in vitro cellular response, we have to separate into location, different size, and different seasons. And we also look at the soluble versus insoluble. A lot of people have a belief that soluble part of the PM is probably more toxic because they can get into the body easier. But on the contrary, we see that in most of the cases, the total PM, and this is the size, including the insoluble part of the PM, actually produce much greater response than soluble part, because once the particle is engulfed in the cell, they can stay there a lot longer and produce greater effect. Soluble fraction, once you get into the cell, will be dissipated and disappear and be metabolized or whatever, and so it disappear quicker and produce much less effect. So we had to look at the total PM instead of just the soluble fraction. And this is the correlation between the change in ROS at the 2 different cells according to the different element of the PM. The usual suspect that can produce participate in Fenton reaction are here: copper, iron, vanadium, nickel. These are elements that can participate in Fenton reaction. They can generate reactive oxygen species. And from our data, it appeared that the endothelial cell actually have a little bit more responsive to epithelial cells. So which cell source are responsible? What we find is the traffic and soil that contain iron, copper, titanium, and antimony are related to have better correlation with the ROS production. And to our surprise is that for this particular category, traffic and soil, the larger particle, the larger symbol here, is responsible for much greater effect, correlate better with the ROS production. And regardless of the location we collected, regardless of either summer or winter, but larger particle contributed much greater for this particular component. For residual oil, on the contrary, it's a smaller particle that are dominating and responsible for much greater change in this ROS production, and appear to be winter residual oil is much greater, have a better association with changes in ROS production in these particular assays. So overall, all the size, city, location, season are very important in terms of producing the obvious component that can produce obvious effect in cells, and PM fraction that that produce greater change is actually the larger the coarse particle, the particle between 10 and 2.5, that are producing greater effect than the fine and ultrafine particles. And most likely, the metal in these PM are associated with the changes in ROS production. And more recently, the people are concerned with the California fire, that what is the health consequences of this huge concentration of PM, and these PM actually produce a very strange orange smoke haze in San Francisco. So people are worried, what is the health consequences of exposures? And not only locally in California, but it also can blow into throughout the U.S. and impact it on the Midwest, as long as all the way to the Northeast region. So when we plot the looking at the epidemiology study, we see this at very high concentration. Actually, the health effect is dropping. It becomes less, and so people are wondering if the higher concentration, it did not have the similar toxicities. And indeed, in Bangladesh, when we look at the PM larger than 100 microgram per cubic meter, actually have a less mortality and ED visit, the emergency room visit, than the particle at lower concentration. And we look at further into what is the reason for this change. We find out that most of the lower concentration is when there's a monsoon, and in the higher concentration time is in the non-monsoon when there's no monsoons. So what is the component related to this very different PM concentrations? And in the India continent, they use the crop burning, a lot of biomass burning, before the monsoon arrived to prepare the field for their crop. So because of the prevailing wind, the Bangladesh actually have very, very high concentration resulting from this during non-monsoon season, a lot of very high PM episode. And you look at the composition, and during the pre-monsoon season, you have a lot more potassium-related particle. Those are related to biomass burning, the green area. During the monsoon, those fires got burned, be put out, and the sulfur component actually produce much greater, greater concentration. So if you plot the biomass burning versus the fossil fuel, the red line actually is dose response, mortality versus the concentration, mortality risk versus the concentration of PM actually have greater slope than the biomass burning. So the biomass burning have much less metals in their mass, therefore produce a flattening curve, have a much less dose response curve than the fossil fuel burning. So the composition actually will drive the resulting health effect. And keep in mind that even though these the biomass burning have shallower dose response curve, they usually come at much higher concentration. So overall, they still have a lot of impact in terms of health effect. And this is a quick summary. And fossil fuel combustion during monsoon season are dominated by fossil fuel, and they have much greater health effect during the fossil fuel had much greater effect than the biomass burnings. So overall, composition of PM is very important. We have to look at these carefully in order to figure out what is the source category that contributing to this obvious effect, so we can effectively control the source to reduce the PM exposure. And thank you very much. I would be happy to answer any questions.
Yeah, thank you, Professor Chen, for your wonderful and informative talk related to the air pollution and the cardiopulmonary health effect in animal and in vitro study. Any question from the audience?
Professor Chen, this is Ping Lin. Hi, nice to see you again. I'm wondering, you mentioned that the coal combustion is a major source associated with the plaque formation. And I'm wondering, in your experience, what would be the major source and the contributor, the major component? What's the difference in the proportion of chemical components in coal combustion that cause greater plaque formation?
We did an experiment in Gansu, China. You're probably aware of that. In that particular site, there is a nickel refinery. They use the coal to produce power to refine the nickel. And in the coal, they have arsenic and selenium. They are one or two of the higher dominating species in the PM. And so when we add these component into another PM mixture that do not have the arsenic and selenium, we can see that it restore some of the response to the overall PM exposure. So we believe that arsenic and selenium in the coal combustion probably related to probably contributing more than the other elements in the coal combustion. And keep in mind that PM is many different mixtures. So it's very difficult to say one or two or three component of the critical, but because the amount present in the coal combustion, the arsenic and selenium present in the coal combustion, is probably one of the reasons for the long-term effect. For the short-term effect, some other element may contribute to that, and we did not look at that carefully at this time.
Okay, so any other question? So Dr. Chen, you look at the particle. Have you looked at the gas phase for this coal combustion, biomass, or wood fire?
Well, we did that long time ago. We used to have, I used to work at MIT. So MIT have a great engineer. They produce this coal combustor that we can actually burn any type of coal and do the animal exposure. What we find out is that the coal actually produce much greater effect. We use the same system to burn wood too, and that produce much greater effect than the wood smoke that in laboratory setting. But those experiments are very high concentration and short term. So we haven't looked at that more recently to look at more realistic and in the conditions. The Bangladesh study, Bangladesh actually would be very, or India subcontinent would be very interesting to collect season and looking at, and also we probably will start a collaboration in the coming year with one of the Indian institutes and research institutes. The goal is to set up an animal exposure facility in India to do this type of study, different season, and looking at the contribution from during monsoon and during the non-monsoon season, and see if we can distinguish that. So, so we haven't done that more recently, but we're looking forward to the future stuff.
Okay, thank you. So we already run out of time.
Thank you very much.
Dr. Chen, thank you again for your very informative talk. Okay. So right now we move to the second keynote speaker. Yeah, please, Dr. Lin.
Okay. It's my pleasure to introduce the next speaker. It's Dr. Huang Bingfang, Professor Huang Bingfang. Professor Huang, currently he's the Dean of College of Public Health in China Medical University. And Professor Huang got his PhD degree in Johns Hopkins University in the Department of Epidemiology, School of Public Health. And Professor Huang, he's an epidemiologist and has been trained in the environmental and occupational medicine and the environmental health. And currently his research interests focus on the health effect of the environment. And Professor Huang, he led a research group in the China Medical University and has published a lot SCI paper in great journals. And also Professor Huang also served as an academic many academic editors and editorial board in many international journals. And Professor Huang, his research interest is major in two fields. First, in ambient air pollution and the birth outcome, including the children asthma, autism, and brain disease. And the second is focused on the indoor environment and the children's health. And today he'd like to share his work with us about the combined exposure to heavy metals in PM2.5 and pediatric asthma. So let's welcome Professor Huang for his presentation.
Good morning, ladies and gentlemen. It's my pleasure to share our work, combined exposure to heavy metal in PM2.5 and pediatric asthma. My name is Bingfang Huang from China Medical University. This is our report outline. Introduction. Background. Long-term exposure to heavy metal may cause adverse health effects, including kidney, heart, liver, nerve, immune system, cardiovascular disease, respiratory disease, as well as neuropsychiatric disease. Exposure to environmental lead or blood lead may associate with increased level of IgE, it would be cause immune toxicity and then cause inflammatory disorder as well as allergic disease and asthma. So, according to the CDC in USA, they indicate global prevalence rate of asthma is up to 4.3%. More than 300 million people worldwide suffer from asthma. It is a big global burden of asthma. Then environmental factors will cause increase the level of immune IgE and cause inflammatory response, then cause bronchial response increase and chronic inflammation of airway as well as bronchial obstructions, then cause respiratory disease such as asthma. So, to our best knowledge, probably the environmental factors and the genetic factor will play a very important role in the relationship related to the allergic disease. For environmental factors such as air pollutants, according to the dense study, they found SO2 and NO2 may associate with the asthma. Then, according to our previous study, we look at the prenatal and the postnatal exposure to PM2.5 and found that it may associate with pediatric asthma. And so far, we also know the sex may play a very important role. Boys tend to have a higher risk of asthma than girls, as well as maternal atopy and smoking during pregnancy as well. So, a longitudinal study in Australia that report long-term exposure to occupational heavy metal may significantly decrease lung functions. Then, it probably the blood lead concentration increase will disturb the homeostasis of trace element in systematic circulation and induce oxidative stress. Then so far, the current study mainly focus on occupational setting, exposure to higher level of heavy metals. Then little studies have been looked at the effect of children exposure to heavy metal in PM2.5 during pregnancy and infancy. So our study objective was that to explore the effect exposure to heavy metal in PM2.5 on asthma during pregnancy and the infancy period, and to identify the sensitive time windows and to clarify the ambient heavy metal on lung development. As well as we also try to look at the dose-response relationship, material and method. This is our study design. We pick up 4 main heavy metals in PM2.5, such as arsenic, cadmium, lead, and mercury. Now we try to use in weather research forecasting model combine chemical modeling to estimate daily heavy metal in PM2.5 concentration and corresponding to the maternal address to get each infant's exposure during pregnancy and infancy period. So our study population is located in the Taichung City from 2004 to 2011 and follow up until 2014. Here is our study area in Taichung. The main source for emissions is major steel plant and the coal-fired power plant, and as well as industry and the science park. At the beginning, we include 191 and 330 infants in Taichung City from 2004 to 2011. We exclude multiple births, stillbirths, birth defect, as well as preterm births. Finally, the study population was comprised of 171,281 children in our birth cohort. Then we also have some children that lost to follow-up, but the follow-up rate up to 99.75%. So we also identify about 18.26% the infant with asthma. For health outcome, the definition was that they receive at least 2 consecutive diagnoses from our physicians, either in outpatient or in patient-based records. Here, just show you how to assess our confounding factors. Our confounding factors selection criteria include that they should associate with the exposures and associate with our outcome of interest, such as asthma. So we elaborate socioeconomic status, maternal age, maternal atopy, maternal anemia, and maternal kidney disease may be a potentially confounding factors. So we controlling those factors in the multi-level regressions. Also, you may look at the green circles. They show it probably associated with the exposure, but not associated with the health outcome. For the red circle, they are not related either with exposure or asthma. For blue circles, they associate with asthma, but not really related to the exposure. So we so-called probably it would be the intermediate variable. For exposure assessment, we got top 75 lists of emission source from EPA, and we can estimate new emissions. Then we also combine meteorological initial and boundary condition models to estimate daily concentration of heavy metal in PM2.5 corresponding to the infants using their maternal residential address to estimate the exposure during pregnancy and infancy. So this work has been done by our colleague, Dr. Chuan Yao Lin in Academia Sinica. So here is Taichung City. Then we try to using this approach surrounding Taiwan. The main source for emissions probably is combustion coals that comprise of a couple of the heavy metal in the combustions. So this is the data we got from global forecast system as well as EPA. So here is the Taichung city map. We have a very large coal-fired plant in Taichung, and also some industry and science park located in Taichung City. For statistical analysis, we're using the Cox proportional Hanel model with time-dependent covariance to estimate the exposure may change over times. Then we also try to using distributed lag nonlinear models with so-called DLNM models to look at the sensitive exposure time windows as well as the dose response relationship. So here is our result. So we found the age of onset of asthma is 3.41. Then boys tend to have a higher risk than females. Lower socioeconomic status, maternal age less than 30 years old, and the maternal atopy and maternal anemia is associated with increased risk of asthma. Then, in contrast, we did not find maternal smoking were associated with the asthma. Probably there is small number of the women that smoke during pregnancy. So we using the IQR as an estimation of hazard ratios. So you can look at the distribution for prenatal and postnatal as well as overall exposure concentrations. This figure will just show you the concentration spatial variation in Taichung. This one, arsenic, cadmium, lead, and mercury, the spatial variation in the Taichung city. We also try to eliminate collinearity between the heavy metal exposures. So we try to use correlation coefficient to estimate these effects. We found arsenic and cadmium is highly correlated, and the lead and the cadmium also have a higher correlated. So we cannot put those four elements into the model at the same time. So that's the reason we have to be very careful to look at the correlations to avoid the collinearity in the models. So this figure just shows you we mutually adjusted for prenatal and the postnatal exposure period, and from the lead exposure during pregnancy is significantly associated with increased the risk of pediatric asthma during pregnancy. So this figure we so-called DLMM models, and then we try to look at the most sensitive time windows we found the exposure during the weeks between 1 to 14 and 21 to 40 the risk is significantly associated with asthma. Then we also try to look at the dose-response relationship. We found when the infant exposure over 26 times 10 power of -2 nanogram per cubic meter show a significant association, but later a little bit plateaus. So we also try to consider the heavy metal is a kind of the mixture. So we try to using the multi-component models. Then we so-called co-exposure. As I pretty mentioned before, 4 elements cannot put it together at the same time in the models. So we using such as lead plus either arsenic or cadmium or mercury. They show a very consistent, positively and significantly associated with pediatric asthma. But we did not find they may associate with prenatal, postnatal exposure to any heavy metal exposures. So this figure just show you it is a very solid finding. Find here co-exposure to either arsenic or cadmium or mercury. The lead exposure show co-exposure to either 3 heavy metal during pregnancy may associate with pediatric asthma. So, discussions. We know the exposure pathway for heavy metal may be through air or diet. Drinking water, dust, as well as soil is the source of the heavy metals. Through probably inhale, ingestion or thermal contaminant that then go into the blood or urine or hair, then cause some health effects. So far, our idea is we try to look at the air heavy metals in PM 2.5 through inhalation, then cause the health effects. So we still cannot rule out the other some possible pathway they will exposure to heavy metals. So that's our study's limitation. But when you're using these models, we can explore this effect in very huge population. So that's the main idea. When we compare previous studies, we found our study is quite consistent with the occupational exposure in high dose. So that is our result is consistent with previous high dose in occupational settings. So the exactly biological mechanism for why the sensitive time windows is between 1 to 14 weeks of gestation and 21 to 40 weeks of gestation. So far, it's not very clear. But when we look at the non-development, it probably locates during the stage embryo to pseudo granule and can cure until the evaluations. So we try to using the epi data to find this association, but so far we still need other animal models to support our result work as well as human models. So we hypothesis is that exposure to lead in PM2.5 through inhalation probably will increase the blood level of lead and increase the IgE levels, then cause type 1 with so-called type 1 hypersensitivity, then cause bronchial response increase. Then it also will imbalance free radical versus antioxidants, then cause oxidative stress increase substantially. Then may cause chronic inflammation of airway, then finally cause asthma. That's our hypothesis. So our study also have some strengths because we did not using the selection approach. We cover all birds born in Taichung during the study periods, the study population up to 300,000 birds. So it's we so-called the nationwide population base to assess the effect of heavy metal in PM2.5 and the asthma. We also have very good high temperature resolutions because we have a daily exposure of heavy metal in PM2.5 estimations. And it is possible to look at the sensitive time windows. And we also have very detailed maternal and infant informations. So we can control those important confounding factors in the models. And also our spatial resolution is 2.5 kilometers. I think so far this resolution is good enough for epi studies. So we also have some limitations because for exposure assessment, such as major lead, arsenic, mercury, or cadmium in PM2.5 is very expensive and time consuming. So we are not be able to get daily observations for long times. We only can get the short time, probably is 2 weeks or 3 weeks measurement during in different seasons. So this model have some limitation to do the validations. Then we also have some possible selection bias because we follow up the children at least 3 years and up to 11, but some children may not is long enough to develop the asthma. Then we also know that maternal may change their residential address during the study period, but so far we only have the data at the birth who born in which residential address. So the other issue is genetic factors may also play a very important role but we cannot control those important factors into account. But we have a prenatal atopy to do a surrogate representative the genetic information through the mothers. So this is our study's limitations. So our conclusion is that the study probably provides a new evidence the effect of heavy metal exposure in PM 2.5 on the development of pediatric asthma, and the lead co-exposure to static cadmium or mercury during the early and the late gestational weeks show a significantly association with increased instance of pediatric asthma. But we know this is the very early pilot studies. We still need the other study to verify our findings. So that's our today's presentation. Before I end my presentation, I would like to thank my two students, Jia Yun and Chaoren Zhong, as well as my colleague, Chuan Yaolin from Academia Sinica. We work together and get this work done. Thank you very much for your attention.
Dr. Huang, thanks for your presentation and very informative. And we have a question from the audience. Okay, I think Dr. Liu. His question is, you mentioned that the heavy metals are from different sources. And can you tell us how did you identify the personal exposure to heavy metal from PM 2.5?
Okay. This idea is I so-called the source is only picked up from major source from 75 days from EPA. So the main source is from our power plant or industry plant. So it's most of the pollutant is from our coal fire. Is called combustion. So that's the reason we try to look at only 4 heavy metals because they cover about 90% combustion from coal. So that's the main idea. Then the other issue is we try to use in some initiators from weather parameters. Then this approach is developed from Academia Sinica from Lin Chuanyao 教授. So we try to using their air pollution map. The resolution is up 2.5 kilometers square. Then also the temporary resolution is daily. So that's the reason we can look at each children, combine their mother's residential address from birth, from conception through birth after 1 year. So that's a main idea. We try to use in their estimation that combine our address and to look at very detailed sensitive time windows. That's the main idea.
Thanks. And any more questions from the audience?
Yeah, I think the audience have asked Dr. Huang, thank you for your wonderful talk. And congratulate that you already published this paper, this study in the high-ranked journal. And I look at the one main table and you find the lead is the main culprit to cause asthma. But if you look at the postnatal exposure, actually, there are some negative association and reach to the significant. Can you explain that?
Because we try to controlling prenatal and postnatal simultaneously. So that's the one way. It's probably highly correlated. So we try to look at the correlation between prenatal and postnatal. They show up to and the correlation coefficient is up to 70. So I think probably is one reason. When you using the when we try to estimate the hazard ratios independently during pregnancy or infancy, the association a little bit consistent for positive. But when we try to mutually controlling for that, one show positive, then the others probably show the negative. So after that, we try to consider the exposure for weekly maybe correlated each other. So we finally decide not just for time-dependent mutually controlling for the prenatal and the postnatal period. We also using with so-called nonlinear models try to see the effects. So after that, when you see the map for probably in the DLMM models, they show the positive association is during pregnancy, not for infancy period. But the association is a little bit varied, but not show very clear positive result. So probably the main result is the lag response relationship. So that's we try to use in two different models to show our data. So when you look at the model one, probably you will see one is positive for during pregnancy, then the others show protective association in infancy. But when you look at the whole period, the finding is mainly in the pregnancy period during this 1 to 14 and 21 to 41 weeks. So that's the main idea.
Okay, and we have a lot of questions from the audience. And the first is Dr. Chen Longjie asked, what is the source of the coal used in the power plant? And is there any plan to use the coal with less metals? 大头黄，你可以看聊天区那个地方有留言。OK， 陈荣基老师问说，那个 coal power plant 用的 coal 的来源 ，what is the source of coal using plant？ 然后可能用比较少的金属的 coal 吗？好，那其实 another audience asked what form of arsenic did you measure? What arsenic is oxide or trivarium, whatever.
Okay, the core probably we can using non-lead core, but actually in Taiwan, if you would like save some cost, the cost quality is still some problem. But so far, we try to ask our government or our power plant to using the more clear core to generate our electricity. But actually, our goal is try to using the 天然气 for gas rather than using coal to get the electricity, and also try to looking for some clear energies. Then the other issues is the arsenic. We cannot distinguish three or two. It's just a mixture. So in this study, we put it together, cannot distinguish which form. So that's our the other main limitations for the simulation approach.
Okay, and Julie has a question about, she asked, did you look at the, let me see, sorry. Atopic dermatitis in children? Yeah.
I think it's the other projects. Actually, it's possible to look at the atopic dermatitis, but I found the other research team, they also did this work and published already. So that's the reason I did not show this result in this talk.
Okay, and one more question, I hope. Okay, and food, the audience, one of the audience asked, the food may be the major, a significant exposure source of these metals, and how to distinguish the exposure, the food exposure contribute to the personal diet, from the personal diet. The food,
So,
how did you?
in our study, I think we are not able to consider the food consumption may contain some lead. So this is our limitation. So in the other way, probably we also can using some food items and try to look at if any possible for lead contaminants through injection. So in our study, I think we have not able to answer this question.
Okay.
So Dr. Fang, in your study, did you have the personal information? Because I find out that you have the cigarette smoking information. So I'm just wondering, how about secondhand smoke?
Actually, this is maternal smoking during pregnancy. So we did not do the personal data collection. It's through our birth registration. So that's the reason some personal information cannot get it in these studies.
I have the last question from the audience. In the multiple exposure model, and you found a significant positive association between air pollution exposure during the prenatal period and asthma, but significant negative association, okay, during the postnatal period. So do you have any comment about the negative association during the postnatal period?
I said it's not really negative association because we are controlling for the same exposure for postnatal and prenatal at the same times. That's cause the collinearity, where cause this result is a little bit strange. So finally, we're using the second model, I so-called the DLMN models, and try to look at the whole periods from prenatal and postnatal, and through the whole process in weekly. So the weekly results show the positive results only in pregnancy. For the postnatal period, they show a little bit association, but not really negative and protective. So my point of view, probably the second model is more appropriate to analyze those kind of data.
Yeah, there one more question come from the audience 2 minutes ago. The question is, okay, in country without lead exposure, will the prevalence of pediatric asthma still increase? And he asked, how can you explain this?
But actually, for our previous study, the main source is probably PM2.5 is the one risk factor for pediatric asthma, will cause the pediatric asthma increase substantially. But actually, we try to look at the components. That's our idea. So probably for asthma, I think the environment will play some roles, as well as the climate change, something like that, or even the heating or too cold. So in our point of view, probably the environmental factors should pay more attention on that, because the genetic factor did not change over time, and they will not cause the asthma increase substantially.
Okay, I think, okay, because of time limit, we have delay for 5 minutes. No. So let's thank Professor Huang again for his excellent talk. And so we will have a break after this section.
Thank you.
Okay,
thanks. Okay. Thanks again for Professor Chen Longji and Professor Huang Bingfang. So wonderful informative sharing and discussion. And thank you, Professor Wu and Professor Lin, great introduction. Okay. So 谢谢陈龙基教授还有黄平方院长为我们带来这么精彩的报告，这样，然后也再次感谢我们的一个主持人吴医师还有林研究员的一个介绍跟讨论。Okay. So due to a slight delay in this meeting, so let's rest for maybe 15 minutes. The next speech will start at 11:20. Thank you. 因为这次会议时间有稍微 delay， 所以我们先休息个15分钟，然后下一场将在11:20开始进行下一场的演讲。谢谢大家。 Okay, ladies and gentlemen, and now for the third keynote speech. Speaker is Dr. Chen Lingzhi. We are honored to have Professor Zhuang Hongyi of Kaohsiung Medical University and Dr. Chen Yuzhen of National Health Research Institute serve as our moderator. Now, let's welcome Professor Zhuang and Dr. Chen. 此次大会我们第3个讲者是中研院陈林志研究员，然后我们大会很荣幸邀请到高雄医学大学公共卫生学系庄弘毅庄医师和国家卫生研究院环境医学研究所陈玉正副研究员担任主持人。现在让我们先欢迎主持人庄医师和陈副研究员。
嗨，大家好。Hello, everyone online. Okay, I'm Hongyi Zhuang from Kaohsiung Medical University. Now I have the honor to present online, and it's my honor to introduce Professor Lingzhi Chen, 陈林志研究员。Lingzhi Chen, the topic is Internet of Things for Air Quality Monitoring, past, present, and future. Professor Chen has much experience on air pollution data. So currently he serves in our academia Sinica, in the Institute of Information, and he served as a director in the institute for coordinated data, scientific data of air pollution. And now he has a big project, so-called Airbox project. It's including 59 countries. So we are very happy and very honored to invite Professor Chen Lingzhi研究员 to come to our conference and to present the air pollution data monitoring, air quality data monitoring, especially at the present and in the future. So let's welcome Professor Chen Lingzhi研究员. Thank you.
Hello everyone, this is Lingzhi Chen from Academia Sinica, Taiwan. Today, the topic of my talk is the application of the Internet of Things in air quality monitoring. I will use our project called Airbox as an example and discuss how the Internet of Things can be used for air quality monitoring, as well as how we make sense of Airbox data to address problems that most people are concerned about. Before we start, I think we should give a brief introduction to the Internet of Things. The Internet of Things is composed of multiple sensing devices, which are connected to the Internet through various methods, such as Wi-Fi, Bluetooth, 3G, 4G, and 5G. Each device measures its use and contributes to the backend database at a predetermined rate. The backend server receives the data stream from all the sensors deployed in the field, which will soon become a large-scale time series or spatial temporal data stream, which can be visualized, processed, and analyzed to provide insight into the overall scenario. In addition, using the collected big data, we can also apply all kinds of AI and machine learning techniques to even deepen our investigation and figure out the knowledge, wisdom from the data. Today, you may have heard many so-called smart blah 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 applications, such as smart city, smart healthcare, smart home, and so on and so forth. And these smart blah 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 are all built based on the Internet of Things to collect data, process information, and generate knowledge, wisdom from the data. This is why we call it smart. In this presentation, I will use our Airbox project to show how the Internet of Things can help air quality monitoring and how much we have achieved using the data collected from the Airbox deployments in the past few years. Let me show you some quick facts before and after our deployment in the next slide. As you can see, Before we started the Airbox project, if Taiwanese were interested in air quality data, they could only rely on 77 professional EPA stations, which will give you the measurement results every hour. However, today, if you want to know the air quality in the area around you, we have deployed more than 12,000 devices, and each device returns a measurement result every 5 minutes. It is conceivable that under very intensive deployment and frequent sampling, we have greatly reduced the spatial and temporal granularity of air quality monitoring, so we can answer people's inquiries about air quality in their microenvironments. Of course, since our system uses low-cost air quality sensors, it may lose some accuracy if compared to professional EPA stations. However, it has also proven to be a good research problem for big data analysis and artificial intelligence, and I will show you how we have overcome these problems in the following slides. Now, let me take a few minutes to take a quick look at the development process of the project. Our project had 3 components. The first one is to enable this technology and make low-cost air quality sensing possible. We started this project from scratch 7 years ago and gradually learned how to assemble sensors, how to make PCB boards, how to use Wi-Fi, Bluetooth, 4G to send sensor data to the outside world, and how to use 3D printing to design the housing. We also evaluate various low-cost air sensors for professional equipment and find good quality sensors that can be used in our projects. Fortunately, we found a low-cost PM2.5 sensor with good performance. The second component of the project is to empower people to use this technology and copy our work to make their own work. We decided to use open hardware, which is commercially off the shelf and easy to be used and even modified when needed. We also published our source codes on GitHub, so people can track and even contribute our codes. Finally, we decided to publish all the collected data in an open data format and in real time. There are several reasons for this. Number 1, we hope to reduce technical boundaries so everyone can easily join us. Number 2, we want to build trust between the participants and our team because everything is open and public. Number 3, we hope to recruit more diverse people. For example, people can join our project by making devices to contribute data, fixing our codes, or contributing new features, or just using our data for their research or developing new applications. In addition, we have designed multiple visualization tools to help people understand the data collected from the Airbox project. We found it very useful, especially for using our system to promote citizen science. The third component is to engage people to participate, collaborate, and contribute. The project was originally an academic research project, and then we worked with a local community called Location Aware Sensing System to recruit people from different backgrounds. Then, we were fortunate to receive a 4-year government grant to deploy Airbox devices in every K-12 school in Taiwan. The focus of the project has also changed over time. At the beginning, we focused on sensor deployment, and then turned to data analysis after collecting a large amount of data from the deployment. Now, we focus on interdisciplinary cooperation to solve real-world problems. Therefore, the project has established a very active and healthy ecosystem involving academia, communities, industries, governments, educational schools, and teachers. These 5 components voluntarily contribute to the system and help each other to keep the ecosystem circulating. To date, the project has deployed more than 12,000 devices in 59 countries. We have established close collaboration with major research universities in Taiwan and have close collaboration with other major low-cost air sensing projects around the world, such as the Array of Things project in Chicago, the AQNU project in Utah, the Smart AQ Net project in Germany, the City Air project in Russia, the Dustboy project in Thailand, and Purple Air in the United States. In addition to deploying and setting up the network, we also put forward some research results. For example, we propose a comprehensive evaluation that compares our equipment with professional equipment and evaluates the consistency performance between Airbus devices. Of course, the results are very encouraging and promising. In order to handle thousands of real-time IoT data streams, we have also developed a powerful backend architecture that can monitor a large number of devices, correctly store the data in different databases, and publish the measurement results in JSON or CSV format in real time. Using the collected data, we implemented an inverse distance weighting algorithm to interpolate the air quality between Airbox devices. We took a snapshot of the visualization results every 20 minutes and made animations to visualize how the air quality distribution changes over time. For example, on the right-hand side, the animation shows the long-distance transmission of dust and pollutants from north side of Taiwan to the south side. The animation was produced in January 2017. This is the first time in history that we can crowdsource low-cost air sensor data and visualize such pollution events with such granularity. In addition, the second animation was shot during a cultural event in central Taiwan. During the event, people burnt incense and ghost money almost at the same time to celebrate the birthday of the most important god. As we can see in the animation, the air quality in central Taiwan turned purple, indicating the PM2.5 concentration was very high, and turned back to orange color after the events. It turns out that it's the perfect material for environmental education because human behavior may affect our environments, especially when a large group of people do things together. We also considered the data quality issues in our system and implemented an anomaly detection framework called ADF to use spatial temporal data analysis to detect pollution events and abnormal devices. This work is actually very challenging because several reasons. One, the accuracy of the device is not as good as that of the EPS station, so our solution must tolerate slight errors in the data stream. Number two, the device is not time synchronized, so our solution must implement the concept of time window slice in our data analysis. Number three, the solution must distinguish between outliers and air quality events, even if they have similar patterns in the time series data stream. And number four, the solution must be simple and fast in order to be able to support online calculations and publish results in almost real time for further applications. The idea of our method is to detect two types of anomalies from the sensor data streams. The first type is called spatial anomaly, which means that the Airbus device behaves differently from other nearby devices. The second type is called time anomaly. That means the measurement data of airbox changes drastically in a very short limit time. Based on the frequency of these two types of anomalies, we can calculate the critical values of each airbox device. And based on the appearance patterns of these two types of anomalies, we can infer the cause of this anomaly, such as the device is located indoors, there is the fixed source of emissions near the device, or a burning event is occurring near the equipment. As you can see in the figure, we have successfully implemented our anomaly detection framework and released our analysis results to the public almost in real time. And the results of our analysis were imported by Taiwan's hacker community, Zero Government, and they create a very beautiful data visualization on their website. In their design, they provide different icons to represent airbox devices with different attributes so that people can easily understand that the devices when viewing the PM2.5 map website. We also applied machine learning to the airbox dataset and contribute on PM2.5 data prediction research to predict short-term PM2.5 concentrations. Here, I mean prediction the PM2.5 concentration in the next 1 to 5 hours. Compared with the traditional data prediction problem, short-term PM2.5 prediction is very challenging because you must train the model, update the model frequently, and give the prediction results in a very timely manner. For example, you may only have 1 minute to complete the entire work and generate prediction results for 10,000 airbox devices. To solve this problem, we consider the solutions in 2 dimensions. One is accuracy, which means we want to have a solution that can provide us with as accurate results as possible. To this end, we have applied modern machine learning techniques such as neural networks or even deep learning to achieve high precision predictions. But the training phase may take too much time to make this solution feasible for our purposes. And the other dimension is scalability, which means we want to generate predictions in a limited time frame for as many airbox devices as possible. For example, we can model the prediction problem as a matrix optimization problem to find a transition matrix between 2 consecutive time slots. Then we can apply the transition matrix to generate data prediction results for the next time slot very quickly, even though the error is also becoming larger and accumulated. Obviously, these 2 dimensions are contradictory, and there must be something in the middle between the 2 extremes. So, we studied different clustering techniques to identify different airbox groups with similar spatial temporal behavior and trained models for each group. And then, we applied this model to other airbox devices in the same group to generate prediction results. As you can see on the figures, the calculation time has been significantly reduced using our method, while the accuracy performance is still acceptable. This is just an attempt to strike a good balance between accuracy and scalability, and more research on this topic is still in progress, and we hope that there will be new results very soon. Next, once we obtained the real-time PM2.5 data from intensive deployment and short-term forecast data from forecasting services, we developed a new navigation service called Clean Air Routing to provide people with minimal PM2.5 exposures routes in the city. by talking about minimal PM2.5 exposure, we are talking about the total amount of PM2.5 accumulated over time during your movement. As you can see, if you want to move from the red dot on the right to another red dot on the left, Google's shortest path algorithm will provide you with a great path. However, our clean air routing algorithm will provide you with a blue route that will turn to the riverside and then to the downtown city, where there are very few vehicles at that time. The total PM2.5 exposure score dropped from 75 to 59, but the travel time was about 30 minutes longer than the shortest one. The clean air routing application is just an attempt to design an innovative application based on a low-cost air sensor IoT system. By providing more fine-grained spatial temporal measurement data, we believe that more and more new applications will be created, and these applications will enable data-informed decision-making in the long run. These applications are very important to IoT systems, not only because they would not be possible without IoT deployment, but also because they can understand IoT systems and make the IoT visible to the public. Recently, we also work with cross-disciplinary experts to address classic problems in other fields. For instance, in spatial statistics and public health, it is essential to predict ground-level PM2.5 concentrations using nearby air quality station data, and the results can benefit health impact assessment of cohorts with PM2.5 exposures. Traditionally, the prediction considers EPA station data, meteorological data, and the spatial attributes. On top of the state-of-the-art, we consider data from the airbox network and adjust the interpolation parameters based on airbox data analysis. The results are very promising, as the R-squared value is more stable at 0.787, and the RMC is reduced to 4.1 microgram per cubic meters. The result of this study may benefit many ongoing public health studies in finding the correlation between PM2.5 exposures and different diseases, and we are still working on improving prediction accuracy of the work and looking for collaboration too. Currently, we have also established a dynamic calibration framework in cooperation with Taiwan's EPA to calibrate low-cost airbox data. First, we selected 31 EPA sites as reference points, and each site deployed 2 airbox devices to conduct a parallel comparison testbed. Then, for each reference site, we considered more than 200 model configurations and selected the one with the best accuracy performance as the reference site's calibration model for that day. Then, for each airbox device in Taiwan, we find the reference site closest to the device and apply its calibration model to the airbox. We understand that there may be some models that can provide even better accuracy performance in calibration, but given our limited knowledge and computing resources, this is the best effort we can achieve so far. Based on the calibration data, we also give activity suggestions when we release the measurement results to the public. In addition, we also publish the model on the website in binary form, as well as detailed parameter configuration so that people can reproduce the results. We believe that keeping everything open during the calibration process is very important because this is the best way to build and maintain public trust. This is also important for the research community because we need to ensure that the results can be reproduced in the future. So far, I have shown you some research results of airbox. Next, I want to share with you some interesting findings that we learned from experiments when promoting citizen science and environmental education. For example, we can use the mask of different materials to package our device and understand which mask material can best prevent PM2.5 exposures. We can also use our device to measure the PM2.5 concentration before and after turning on the air purifier to compare the performance of different models of air purifiers by crowdsourcing tests to the community. We also installed airbags in my vehicles and conduct a very simple experiments to study the air quality of the interior recirculation and exterior air. This airbox is the special version made by my team. It has PM2.5 and CO2 sensors. When I got in the car, the PM2.5 and CO2 readings were about the same as the outdoor conditions. And I started using the internal air recirculation drive. As you can see on the slide, the PM2.5 curve slowly drops because the air inlet is equipped with the filter, and the air is getting cleaner after being recirculated. However, you will find that the CO2 curve grows very fast, reaching 2000 ppm after 20 minutes. We know that after a period of such high concentrations, people may feel sleepy and inattentive, which can be dangerous when driving at high speed. Then I switched the air conditioner to outside air mode, and the CO2 concentration quickly dropped to less than 700 ppm in just 3 minutes, which was acceptable. The PM2.5 level also increased to 32 microgram per cubic meters, which is approximately equal to the outdoor PM2.5 level. It turns out very interesting that when driving on the road, we need to switch back and forth between air recirculation and fresh air mode, so that we can achieve a good balance between energy saving and good air quality in the car. So, what's the next step for the Airbox project? There are still many open challenges ahead. For example, in terms of equipment hardware, we hope to integrate additional sensors into the system, such as CO2, TVOC, sound, and light sensors. We hope to study energy harvesting on Airbox and make the system self-sustaining in the future. We hope to strengthen the security design of our system and gradually offload some data analysis and machine learning tasks to edge IoT devices for edge computing. In addition, in terms of big data, we hope to deepen our research on multi-source data fusion and use cyber-physical social data as a whole to understand the interaction between the environment, the cyber world, and the social media. We hope to cooperate with environmental experts and apply artificial intelligence technology to strengthen model-based simulation research. We hope to combine AI technology and GIS applications to form GeoAI and embed this intelligence into future database systems. Finally, in terms of applications, we hope to shift the focus to indoor scenarios and promote more interdisciplinary research, collaborations, and international cooperation. We hope that all these efforts will help to promote data-informed decision-making in the near future. Okay, let me end this conversation. In this talk, I introduced an application of the Internet of Things in air quality monitoring. The project is called Airbox, and there are several lessons that we learned from the project. Number one, open is the key to making things possible and making the overall solution scalable. Number two, the power of the Internet of Things is to make sense of data. Number three, there are many challenges and research issues in the future, I encourage you to think about the must-have problems rather than nice-to-have problems, because this is the only way to make your system meaningful in the real world. There are still many unsolved challenges, and I look forward to working with you in the near future. This is the end of my talk. Thank you very much for your attention.
Thank you. 玉正，交给你。
Okay. Thanks for Dr. Chen's presentation. Now we for the open question. Any audience in online or internet? Before someone asking, I have one question. I think the Dr. Chen's IoT project or large project is really successful. Not only researchers or government join this project, but also our community residents. And I heard many people from the Facebook to talk about the large projects. And then my first question is based on your past experience for this project. And could you please share us more stories and about what benefits when our community residents are using airbag sensors or local sensors, and what can they get, and then to improve their air quality? Do you have any story from that?
Okay, thank you, Professor Chen. So actually, there are many stories. So and I think for the low-cost air sensor, it can provide you microenvironment information. So we found many people they use the micro sensor, the local sensor, to know what's the current PM2.5 concentrations in his surrounding area. So if you have kids have asthma or some kind of respiratory disease, then you are very sensitive. I mean, they are very sensitive to the air quality, and you're also very concerned about the air quality. So they use the tool to help them to prevent the exposure to such high concentration, and also to take some proper response. For example, you can turn on the air purifier or close the windows, so on and so forth. So there are many such stories, and yeah.
Okay, and someone asked what price about this device?
Well, it's around 3,000 to 4,000
$20?
PD. Yeah, or say 100 USD. Yeah.
Okay. And someone's asking how to involve people implement collaboration to sensor air population.
You mean the calibration?
No. Yeah. How to involve people implement collaboration. Yeah, to sensor air population.
Okay, so I work with many researchers, and there is everyone has different purpose for this collaboration, but the common interest is open data. So I am happy to provide such tool, such data platform, and I also provide data access. So if you are interested in this project, you can use the machine. They will send data to my server, which is reliable, and I give you the open access to the data. And also we can have more such talk, and I know many experts because many people talk to me. So I know a group of good people like Professor Chen. You are also one of the collaborators. So I think this is a very positive, healthy ecosystem. So everyone interested in local sensor, you have your request, and I can help you even customize the device to provide you some special functions. So yeah, just do it and talk to me if you have any special interest. Yeah.
And how many countries has used this device for air quality monitoring?
Okay, it's very difficult to give you the exact number, but I already observed people from 59 countries.
Oh,
They use
59.
my device. Yeah.
Okay.
I have a question to Lin Zhi. Since it's Internet of Things, how about the DPRO? I mean the database. Does the database open for scholar or research? Thank you.
Well, we have the ones. Well, we have different methods for you to upload your data. Let's haul data from your device to our server, and then we also have web access. We have provide some URL specially created for you. Actually, it's the open API. Well, you can just recruit some student who knows internet programming. They read our document, then they know how to get the data back to your device, your computer. Yeah.
Okay.
Thank you.
I have a really challenging question for you. As we know, the recent big news from the WHO is the announcement of updated air quality guideline beyond COVID-19, okay? For instance, the annual and the 24-hour average concentration of PM2.5 has been subject to 5 and 55 microgram per cubic meter, okay? And I guess no longer the Taiwan EPA would take this guideline to set lower limits of PM2.5. And as we know, the recent air quality in Taiwan overall becomes better compared past, and the PM2.5 concentration go to lower. My question is, the accuracy and the precision of PM2.5 low-cost sensor have been questioned, in particular in detection of the lower PM2.5 level. Could you please comment this new challenge of the low-cost sensor facing lower ambient PM2.5 in the data science?
Okay, it's a very good question actually. So I think it depends on your purpose of using this low-cost sensors. Since it's low cost, so we don't expect it to be super accurate, super precise. It's impossible, right? So we will lose some accuracy, that's for sure. And when we talk about the new WHO's the guidelines, the concentration, PM2.5 concentration is very low actually. And I will say if the air quality in Taiwan is already very good, it's under 10, not 5, under 10, then actually no one needs local sensor. The reason we need local sensor is because the air quality is not good. We want to protect our family. We want to protect our kids. So we want to have early warning system. That's why we need to have local sensor. But if we want to make sure whether we are under the WHO guideline, we still need to go back to professional devices.
Okay. Yeah.
Thank you.
Yeah.
Okay. Does anyone have a question to Lin Zhi? Currently, there's 19 auditor online. So
I have one question.
Yep. Okay. Please.
In your slide, for your next research, it's about the low-cost gas sensor. Okay. Do you have any comment on that or progress research?
Actually, no. I know TVOC is mature enough, and many people are already using it now. And in addition to TVOC, maybe ozone will be the next one to come, but it's still not ready yet for if you want to have very serious applications.
How about the NO2?
No.
No,
NO2
is it possible to develop that?
Well, it's very unstable.
Okay.
Depends if you want to have an NO2 sensor and you agree to recalibrate the sensor every week, then probably you can use it. Yeah.
Okay.
I see Leon online. Leon have any question to Linzi?
Sorry, no, it's a wonderful presentation. Thank you very much for insightful knowledge. Thank you.
Thank you.
Thank you. So it's time.
Yeah.
12. So thank you, everyone. Thank you, online, everyone. We think it's lunch time. So let's end in this section. Thank you, Linzi, and thank you, Yuzheng and Leon.
Thank you. Thank you.
Thank you. Bye-bye.
Thank you, Dr. Zhang.
Thanks for Dr. Chen Linzi's amazing presentation, and thank you, Professor Zhuang and Dr. Chen, great introduction. 我们谢谢陈林志研究员为我们带来这么精彩的简报哈，然后也再次感谢庄医师还有陈副研究员的介绍哈，谢谢。Okay. The session in the afternoon will begin at 13:13. At 13:13, please come back on time and thank you for your cooperation. 早上的议程我们就到此先告一段落哈，那下午的议程会从下午1点30分开始哈，下午1点30分，请大家准时回来哈，谢谢大家的合作哈，谢谢。 welcome back to this conference. And now for afternoon keynote speaker is Professor Guo Yuliang. We are honored to have Dr. Hong Zhixin of Kaohsiung Medical Xiaogang Hospital and Professor Cai Pengzhi of National Cheng Kung University serve as our moderator. Now let's welcome Professor Hong and Professor Cai. 此次大会下午的场次，第一个邀请的讲者为台大郭玉良教授。我们很荣幸邀请到高雄市立小港医院洪志新副院长和国立成功大学工业卫生科技环境医学研究所蔡鹏之特聘教授担任主持人。现在让我们欢迎主持人洪副院长和蔡鹏之特聘教授。
Okay, good afternoon, ladies and gentlemen. I am Dr. Zhixin Hong, Vice Superintendent, Kaohsiung Municipal Xiaogang Hospital. It's my great honor to moderate this session, keynote speech number 4, and to introduce Professor Guo Yuliang. Professor Guo Yuliang is a distinguished professor in Environmental Occupational Medicine, School of Medicine, National Taiwan University, NTU, and attending physician in NTU Hospital. He obtained his medical degree from NTU University and master degree from Harvard School of Public Health and PhD degree in Environmental Health Occupational Medicine from Johns Hopkins University. He served as a residency in internal medicine in Texas Tech University and also in occupational medicine in the University of California at San Francisco. He became a faculty member in medical school, National Cheng Kung University in 1990. In 2006, he became a faculty member in medical school of National Taiwan University until now. He was president of Asia Congress Occupational Health 2002. His research interest has been on the healthy effect caused by environmental agents such as air pollutant, allergen, climate change, and endocrine disrupting chemicals. His research work resulted in more than 320 international papers and 10 book chapters. Today, the topic he would like to talk is air pollutant and diabetes mellitus. Professor Guo, please.
Thank you very much. Do you hear me?
Yes.
Yes.
And do you see my first slide?
Yes.
I'd like to thank my co-author, Dr. Sijun Pan, who is currently working in NIEHS as well. Do you see that turning to the second page?
Yeah. Yes.
Oh, okay, good. There are many health effects of air pollutants, and that would include mortality and respiratory, cardiovascular, and psychiatric diseases. And also chronic conditions like cancer, diabetes mellitus, and congenital conditions. And from the epidemiologic point of view, the more immediate effects are studied more. So the mortality per day and the respiratory effect, cardiovascular, in terms of the attack, is more studied. But a more chronic conditions occurrence takes a longer cumulative exposure, is less investigated, but currently is increasingly understood, despite more still much information to be studied. Diabetes mellitus is an important clinical and chronic condition. As you can tell, the global situation in diabetes is actually, if you look at the, let's see if I can Oh, okay. This is a laser point. So it has become the most important 10 leading cause of death. And there are increment of deaths according to that due to diabetes mellitus in many countries, but the number one being India, China, Indonesia, Mexico, and United States. Recently, a meta-analysis reviewed air pollution and type 2 diabetes incidence. And you will find that PM 2.5 is related to occurrence of T2DM, and that is for per 10 microgram cubic meter increment, about 10% increase. Such effect was not observed in NO2. However, there are knowledge gap, which is the dose-response relationship. You will see this is a typical toxicological dose-response curve, and you will see that it's a sigmoid shape from the initial increment followed by a more straight line, and then most of people have been affected, therefore a slow increase. So what happened is we are always wondering about the no observable effect level. Whether that exists for air pollution is a question. So why do I say knowledge gap still exists, even you know that there is increment in per 10 microgram per cubic meter? Because in the meta-analysis, usually we do not know where in the curve that belong. So the meta-analysis can accumulate information from different dose level and come up with a summary score, but that doesn't know which portion of the curve is important. And if we look at the literature carefully, we'll see that many investigations in the lower dose range from the United States and Canada, some from the EU, some from Asia, but a lot of information related to exposure to PM at PM 2.5 at 20 to 35 have been lacking. That's why I say the dose response relationship is not totally established. And then the NOEL is still unknown. For chronic disease, you would also like to know whether there are a clear dose response like this. So this is a long-term follow-up study in Canada involving more than 2 million people, and hospitalization due to cardiovascular events and stroke are related to PM 2.5 here, ozone here. And stroke is related to PM 2.5 and ozone here. What you want to notice is that there seems to be a straight line increment associated with PM 2.5 and ozone for acute myocardial infarction hospitalization. But that's not true for stroke. There seems to be a threshold. So ozone, ozone is, for example, up to 40 something, you will see more observable effect in stroke. However, in this investigation, you can't totally separate the effect of PM 2.5 and ozone. So cumulate them together, PM 2.5 and ozone contribute to 6% or AMI, 6.8% of stroke. And this is at the 10-year moving average, PM 2.5 or 6.7, ozone of 37.5. So in the PM level, it's rather low, intermediate for the ozone. And however, such effect gives us very good description of dose response, which we do not have yet for diabetes. We participated in a gestational diabetes mellitus study to relate it to ambient air. And this is based on the Taiwan birth cohort study. And we found that there is almost 20,000 women who were pregnant during year 2004 and 5. About 1.9% was diagnosed as having gestational DM, and they are older with higher BMI. It's not surprising. And we found also 1 ppb increment of NOx is related to 2% increment of gestational DM. And if you look carefully among the NOx, the NO itself became most important. It's 1.5 per 1 ppb increment. And this occurs, most important exposure period is the first and second trimesters. So we thought that exposure to higher NO level or NOx level during pregnancy is related to gestational DM. This later got included in a meta-analysis, which show that PM 2.5 is borderline, but probably not significant, related to GDM. NOx is related. NO2 is related. So it is interesting to know that, to found that why are the related pollutants different from those of DM? So the related pollutants for DM is PM 2.5, and for GDM is NO2, is NOx. So we have some knowledge gap there. This is summarized of the mechanism from the several papers. But the knowledge gap is that what are the most important steps that lead to the DM occurrence? Is that oxidative stress? Or is that something happening in the liver or adipose tissue? Is quite uncertain. So we know that air pollutants are related to DM and GDM. Then we have to look, because we not only prevent DM, we like to prevent the complications of DM, which are actually very important medical conditions. So there are microvascular complications like retinopathy, nephropathy, neuropathy, macrovascularly, cerebral vascular disease like stroke, coronary heart disease like myocardial infarction, and peripheral vascular diseases. These are something that we should try to prevent. We look at the effect of renal function, renal effect from air pollution among diabetic patients. This is in collaboration with Dr. Xu Zhicheng from NHRI, and it's a longitudinal study involving 36 clinics and 812 type 2 DM follow-up for more than 3 years. And summarize the finding, the gender, waist girth, HbA1c are related to albumin increment. So more protein in the urine. But we also found that CO from the ambient air and PM2.5 exposure were also related with the IQR and related to 0.2 milligram per albumin per gram of creatinine, and PM2.5 IQR of 9 related to 0.8 milligram albumin per gram of albumin of creatinine. So this is some indication that proteinuria is increased with air pollutants in diabetes. And this is usually what happened to nephropathy. So initially there is a hyperfiltration, the glomerular filtration is increased. Then there was no change in glomerular filtration rate, and then it dropped until end-stage renal disease. And this is a period called incipient diabetic nephropathy. However, you would detect increasing albumin in the urine at this period. I think we found the relationship here. And does it indicate that nephropathy at the end will be increased? I think it's very likely. This is a meta-analysis studying the chronic liver disease, not specifically in diabetic patients, in everybody, but they found PM2.5, PM10, and NO2 to be all related to increment of the chronic liver disease, chronic kidney disease. And this is also associated with reduced glomerular filtration rate in here. So the findings seem to be comparable. And this would alarm us if this is found in diabetic patients with the finding of albuminuria and also the general population with increased CKD. It's most likely that diabetic may be susceptible to air pollutant effect on kidney. This is a study. We investigated the complication retinopathy. What we did was we used a national health insurance data set and look at diabetic patients, whether they develop diabetic retinopathy or not develop retinopathy. So it's a study on the complication diabetic retinopathy and look at their exposure to air pollutants. What we found was from the PM2.5 and PM2.5 to 10, both significantly related to occurrence of retinopathy. And for per 10 microgram per cubic meter, it is 1.29. So it's a large increment, like a 30% increment for associated with the PM 2.5. So I think this is something that indicate complication like retinopathy is related to air pollutants. I'd like to thank the first author, Dr. Pan. And the progression from GDM to DM is well documented, so that the woman with GDM, it's easy to become type 2 DM in the later life. We study in the whether the progression from GDM to DM can be affected by air pollutants. And to make a long story short, PM 2.5 will give you increment of type 2 DM by about 20%. For those who had low exposure to PM and with diabetic GDM, the diabetes increased by about 13 times. If you are having GDM and also high exposure to PM 2.5, the increment is almost 30 times, indicating that the PM 2.5 and GDM act synergistically for later diabetes occurrence. So if we know that diabetes and their complications are related to air pollutants, how should we protect the people? Of course, the single most important is to reduce the exposure through tightened air quality standards and environmental control. However, we know that the threshold is almost non-existent for many chronic diseases, and we are not sure whether it exists for DM. So there are other activities that we should be able to do. Health promotion activities, among those with risk factor of diabetes and among those with GDM, that could probably prevent the occurrence of DM. Active treatment of DM to prevent complications. Whether we should use PPE or indoor protection to protect people when there is high level. And are there effect modifying environments such as greenness in the residential surroundings? These are new topics to be addressed. So there are actually some effect modifier to weaken the effect of PM 2.5 on diabetes, like fruit consumption, like smoking, smoke cessation, and clean heating energies. That's already documented. So these probably can be done. For those who already have GDM, if you do nothing, they progress to DM in a rather fast speed. However, if you do lifestyle modification or provide metformin, then it slows down the progress from GDM to diabetes. So this may be considered, especially in the higher polluted area. Kidney disease can be prevented by a very good ratio, almost a half in the reduction if glucose level is controlled well. And this paper summarizes personal and household protection. For personal respiratory protection, subclinical CV health benefits from well-fitted respirators are documented. However, just face masks or behavior change is a question mark. For household, or this I think I will appreciate Dr. Tsai's input later, the HEPA filter air purifier can reduce indoor PM 2.5 and improve subclinical health markers. However, the author also say only when emission cannot be controlled at the source. For example, forest fire, the individual and household level intervention may be an option. And in most cases, such intervention should be supplemental to emission reduction efforts that benefit entire community. I agree with this. The other thing is, if you want to do the personal protection or indoor protection, when do you want to do it? For example, this is a level with fluctuation of PM 2.5 in 2018. When should we install the PPE or turn on the indoor protection? It's still unknown. And that is due to the lacking of a clear dose-response relationship. This shows the lung cancer relationship by global burden of disease investigators and also the Canadian CV disease. We do not have it for DM so far. Effect modifying environment like greenness is mentioned. However, it's not certain whether it has additional effect except for modifying the air pollution, reducing the air pollution. If there is additional effect, that would be a very important thing to increase your greenness in the surrounding. So I think I conclude very briefly. Who are highly susceptible people? Pretty much no. Are there effective measurements? Some and increasing. At what level? We do not know. But recent WHO guideline say PM 2.5 or 5 microgram per cubic meter, NO2 of 5.3 ppb, ozone of 30 ppb. So there are many issues to be considered and studied. I'd like to end here and thank you for your attention. Thanks.
Okay, thank you for Professor Guo's excellent talk. I didn't see any question on the board, so may I have ask Professor Guo first question?
Yes, please.
Since you measure the relationship between the type 2 DM and gestational DM, because I'm a pediatrician, you look at the type, how about the type 1 DM is also close relationship with air pollutant?
I think it's a good question. I haven't looked carefully into the type 1 DM, so I have to say, please give me some time, and I have to respond to you, and if possible to all audience, whether type 1 DM is related to it. But the type 2 DM is more certain. So sorry, I need to respond to you later.
Sorry, the question is not so good. So,
No. Good. Yeah, it's a good question.
Until now, no any other question on the audience. So I may ask the second question. My second question is any relationship between the air pollutant and the DEM resistance for the drug or insulin?
It's a wonderful question, actually. I don't think there is much information at this moment related to the treatment effect. I think we should use the treatment. I think it has to do with difficulty in carrying out the study. So a lot of study on air pollution been related to the secondary data, because primary data on air pollution exposure is hard to obtain. And therefore, the secondary data, again, has some difficulty in obtaining their the drug medication history and how compliant they are with the medicine. So I'm not sure if there is any data existing for the resistance to medication in the highly exposed population. However, in here, I think from the mechanistic point of view, if the air pollution can affect beta cell and the muscle, liver, adipose tissue, and inflammation, systematic inflammation, I think it's very likely it would affect the medicine that you give it. And my understanding is the metformin not only provide effect in lowering the blood glucose, it also provide some effect in antioxidation, which might be related to the documented GDM to DM effect. So not sure if there is any data, but I believe this study is very important to be done for the near future.
Okay, because we have another moderator, Professor Tsai. So
yes,
any question from Professor Tsai?
Yes, I do have one question for Professor Guo.
Mm-hmm.
I found that the cost fraction of PM, like PM 2.5 to PM 10, and they also have effect on diabetes. So would they have same potential mechanism?
Mm-hmm.
Yeah.
Well, I think this is a good question as well. From what Dr. Chen presented this morning, I also learned a lot from the presentation. There seems to be different components or constituents in the PM 2.5 and 2.5 to 10. And apparently, due to the different constituents in the groups of air pollutants, their effect may be different. Probably because the content of metal, the content of biological burning are quite different. So I would think that the effects are different, but I do not have a very strong evidence so far. I think it's worth investigation for the near future. Thank you for the question.
Okay, thank you.
we still have several minutes. Still no question from audience. So, Professor Guo, may I have the third question?
Sure.
So my question is the air pollutant labels correlated to the blood sugar label? Once the air pollutant is very high, the blood sugar for DM patient will be higher, and clinical doctors should have the much drug to treat the blood sugar.
I think this is also very good. If you like the initial alarming system for the air pollution comes from those with asthma. So those people with asthma, they are more susceptible to attack of asthma to when air pollution levels are high. So they gave up alarms saying that this is unhealthy for susceptible population like asthmatic. And I think my presentation today is to hopefully to let people consider whether we should also provide alarming system for diabetic patients. It's not sure whether it will have an immediate attack like asthma occurs. Not sure. However, in a cumulative way, if you are exposed to higher level of pollutants, the potential of having worse control blood sugar is there. So I think it's a good point. We should consider that, but the alarm need to be communicated. The alarming system has to be communicated between the health authority and the environmental authority to make the decision.
Okay, thank you for your good answer. Because time is up, we should move to another session, moderated by Professor Cai Pengzi. Professor Cai, please.
Okay, thank you. So we're going to next presenter. Keynote speaker, is that right? Okay, I find Professor Wu is there. Yeah. So may I introduce Professor Wu? My name is Pengji Cai from National Chegang University, and it's truly my privilege to introduce you our distinguished keynote speaker, Professor Chida Wu. Chida Wu got his doctoral degrees from National Taiwan University, major in forestry. He now is an associate professor in the Department of Geomatics, National Chegang University, Hainan, Taiwan, and also a associate research fellow in NHRI, and also a director of Chinese Society of Photogrammetry and Remote Sensing. And Professor Wu have very wide research interest. Most importantly, in the air pollution modeling, air pollution health risk assessment, and health benefit of surrounding greenness. And Professor Wu has published more than 60 SCI papers. Today, his topic is for the presentation is using land use machine learning models to estimate daily NO2 concentration variations in Taiwan. Let's welcome Professor Wu.
Okay. Okay. First, thanks for the introduction from Professor Tsai. And Professor Tsai, Professor Hong, our chairperson, and ladies and gentlemen, thanks for coming to my talk. I am Wu Zhida. I also have an English name Zhang, so you can also call me Zhang Wu. And just like the introduction from Professor Tsai, I am now teaching in the Department of Geomatics at National Cheng Kung Universities. And I also have a long-term cooperation with the NHRI. So I also serve as an adjunct associate research fellow in NHRI. Actually, I mean, students in our department, they learn diverse technologies. Let's say, for example, our students learn GIS, the Geographic Information Systems. They also learn how to prepare the satellite images and also apply satellite images on different topics like the environmental monitoring. We also learn big data analysis. We use machine learning to fit a model to monitor the environmental changes, and we also learn some statistical spatial statistics skills. So for me, personally, I mainly apply this kind of geospatial technologies on two topics related to public health and environmental health. The first one, my first research interest mainly focused on air pollution modeling. And the second one is I want to understand how much people exposed to the surrounding greenness. Then I apply this kind of information like the air pollution exposures and the surrounding greenness exposures to see what are the linkages between the environmental exposures with human health, the effects on human health. So this is my research expertise and research interest. So first, I would like to thank for the long-term support from the NHRI. So I have been joining the research projects conducted by led by the NHRI for more than 8 years. So we mainly focus on the air pollution and air pollution health effects. So my role in this team is, let's say I should say that I'm a modeler. So I just use the technologies I introduced to you, like GIS and remote sensing. We try to apply this kind of technologies to estimate the spatial and also the temporal variabilities of air pollution in Taiwan. Then our collaborators and our partners in this team, they just use my data to assess the potential health impacts from air pollution on human health. So in the past 8 years, we also have proposed several approaches to make the air pollution prediction better and try to predict the air pollution variability more accurate. So basically we propose 3 approaches. The first one is a localized AUR model, and the second one is a hybrid region AUR model, and the third one we try to apply the machine learning to develop a machine learning based ensemble model for air pollution predictions. We also have published several papers related to this kind of methodologies. So the first approach is we try to incorporate some culture-specific emission sources factors in the land use regulation modeling. I mean, if you check a reference related to land use regulations in the Western cities, you will see the main factors they consider in their model, just like the traffic, industry, of course, the household, the residential areas, and also maybe sometimes they also consider about the effects from the thermal power plants. But if you go back to Taiwan or just you go back to the other cities in Asia, you must know that we have diverse culture-specific emission sources distributed at the community scale. For example, we have emissions from the incense burning. We also have emission from paper money burning in the temples. And if you go to the night market in Taiwan or the other Asian country, you will see people use a big fire for cooking, and the emission from cooking is really a big impact on our air qualities. So in our model, the localized land use regulation model, we try to incorporate this kind of culture-specific emission sources like Chinese restaurants and the temples in our model to well depict the spatial variability of air pollution in Taiwan. So we also have applied this kind of methodology in several types of air pollution like PM2.5, ozone, PM2.5 constitutes. And my students from Indonesia, they also apply the same strategies to assess the PM10, PM2.5, and also nitrogen dioxide to assess their spatial variabilities in Indonesia. And in the second approach we propose, we call this one as a hybrid model. So in this model, we try to incorporate land use regression with spatial interpretation like kriging. We try to combine these two methodologies together. Basically, the idea is to incorporate the kriging interpreted air pollution levels as the predictors in the land use regression models, then try to improve the model performance by this kind of combinations. So 2 papers have been published by using the hybrid models. We focus on the PM2.5 and also nitrogen dioxide for the whole island, for the main island of Taiwan. And then now let's move to the latest approach we use. So this time we try to combine all of the strengths in approach 1 and approach 2, and but this time we don't use linear regression to fit the model, because you know, in the conventional linear regression model, people usually use multilinear regressions to develop models, but you know there are some limitations by using the linear regression model to develop to assess the relationship between air pollution levels and the predicted variables, because it's not easy to depict the nonlinear relationship by using linear models. So this time we don't use a linear model, but instead of that, we use several machine learning algorithms try to improve the model performance. So this kind of machine learning based model have been applied in several cases like the PM2.5 and also nitrogen dioxide. This is also the case I want to talk in details to you later. And we also try to assess the spatial variability of carbon monoxides in Taiwan, and also we also try to focus on the VOC variabilities in the Kaohsiung industry areas. So now we have air pollution prediction from our model. So I just try to work together with several very outstanding researchers from different countries and from different research institutes. We work together and we will try to see how does the air pollution exposure affect human health. So here we consider not only the physical health, we also have some study talk about the mental health. And of course, we also try to deliver the scientific findings we learn from these studies to our, just like the governmental agencies. We hope this kind of information will be helpful for the EPA, Taiwan EPA, to improve the air quality in Taiwan, and also to improve the human well-being in Taiwan. Okay. So let's move to my major topic today. So here today, I want to introduce I want to share one of our recently published papers. In this one, we just try to use let's say the best approach we have developed. We use a machine learning based approaches. This time we want to see how does the machine learning model could depict the NO2 variabilities in Taiwan, and whether we can use this kind of approaches to to accurately estimate the NO2 variability for the whole island of Taiwan, and also for long periods for around 2 decades. And this paper has been published on the Journal of Cleaner Production in this year. And I would like to show my appreciations to all of our cooperators, like the Professor Huizhen Su and Professor Huang Renwei from NCKU, Professor Li Xiaoyun from the National Taipei University of Nursing and Health Science, and also we also have a cooperator from the Professor Zhang Zhian from the National Jiao Tong University, and also Professor John Spanger from Harvard School of Public Health. And the first author, Peiyi Wang and Wang Peiyi and Xiao Yaping, they are my students. We work together so we can have this kind of findings. So, okay, so now we know everybody must know that air pollution is becoming a growing concern issues in recent years. So we have different types of air pollution in the air. Let's say we have particle pollutants, but we also have gaseous pollutants. Among the gaseous pollutants, I think the nitrogen dioxide NO2 is a very important gaseous pollutant, and particularly in the city areas, because we know the major emission sources of nitrogen dioxide is from fossil fuel combustions. So, for example, in Taipei City, this is also the capital city of Taiwan. We have a very busy traffic, and we have a very high populated area in Taiwan. So this kind of situation will we might also face a big challenges from the nitrogen dioxide's impacts on human health. So this picture just shows you the spatial distributions of air quality monitoring stations in Taiwan, launched by Taiwan EPA. So basically, we have around 76 monitoring stations for the main island of Taiwan. But you can see we have very limited number of monitoring stations in the eastern part of Taiwan. We only have 1, 2, 3, 4, 5 monitoring stations in the eastern part of Taiwan. So we don't really know the real exposure level for people they are not close to the monitoring station, right? So even though we have more monitoring stations in the western part of Taiwan, because most of the major cities located in the western part of city of Taiwan, but you can see the number is not good, or the distribution is also kind of a sparse distributions. So in this case, if you directly apply the measurements from these monitoring stations and to link the air pollution air pollution measurement from this monitoring station to the human health, you might find some challenges. I mean, for example, you might face a challenge about exposure miscalculations because we don't really have a monitoring station for everywhere. And also, when you conduct the health risk analysis, sometimes we might also have problems in overestimate or underestimate the health risk from the air pollution exposures. So in this case, sounds like we must need a more efficient way to estimate the air pollution variabilities for the whole island of Taiwan. So many spatial modeling approaches have been proposed in the past years, but let me say, one of the most popular approach I think might be the land use regressions. So this picture just try to illustrate the major idea of the land use regressions. So we have the measurements from the monitoring station no plot, and from GIS and remote sensing. This is my major expertise. We can know the spatial distribution and the spatial allocations of emission sources surrounding by the nearby the monitoring stations. So in this case, we use GIS and remote sensing to obtain the land cover emission sources distributions. We use this kind of information as predicted variables. Then we use the measurements from the monitoring station, from the field station as the dependent variables. So people in the past year, people simply apply the multiple linear regression to develop a prediction model. So in the case, the model, the prediction performance is good. So we can just apply this kind of land use land cover information to predict air pollution levels for non-major areas. So this is the basic idea of the land use regressions. Because we can very easily to obtain the data from GIS and remote sensing. So you can say this methodology, I mean, the land use regression is very easy to be used and very convenient, let's say, in general. So by here, I mean, I also want to highlight one more strength by using the land use regression, because the statistical analysis provides us a very useful way to identify the important predictive variables. For example, we can use the p-value, and we can use some statistical criterion to identify whether this predictive variables is useful or is statistical significant to the air pollutions. So, I mean, land use regression, the other strength from land use regression is to, let's say we can call this as a variable dimension reductions. We can try to figure out which variables are useful, which variable they might not make sense to be imported into the model. So, I mean, this is also one strengths I want to highlight about the land use regression. But just like I mentioned to you in my very beginning part of the presentation, a linear model is not a good way to depict a nonlinear relationship. For example, for some predicted variables, they don't really show a linear trend with air pollution variations, but they might show some nonlinear trend. But in this case, a linear model might not a good tool to develop a model. So recently, I mean, the rapid development of machine learning provided us new solutions to fit a more complicated linear or nonlinear relationship between the land use land cover emission sources and the air pollution levels. So this kind, I mean, people start to apply different type of machine learning algorithm to develop the predictive models for air pollutions. But one of the biggest challenges, I mean, in the past year for applying the machine learning model to develop model is about predict variables. Because in the conventional machine learning approaches, they don't really have a way to identify, to filter out the important predicted variables. That indicates if you have 600 predicted variables, machine learning algorithm just take all of them into the models, then use all of the 600 predicted variables to develop the model, then show you an outcome, the prediction from the models. But you don't really know the real association between each predicted variables with air pollutions, and you don't really have a way to reduce the dimension of the predicted variables. So this is also that indicates we need to find a new way to overcome this kind of challenges. So in this case, in my study, I just try to combine the strengths from both the linear regressions and the machine learning. So first, we use the linear regression models to filter out important predicted variable. I just simply use the very widely applied variable selection approach. We use the stepwise variable selection procedures and UR. So during this step, we try to identify the important and also the variables with right directions with air pollution. Only this important and the important predictables will be kept in our database. Then in the second step, we use these selected variables from the statistical strategies. Then we apply this variable to and also couple with the machine learning algorithms to develop the prediction models. So now we have a benefits, we have a strength from the UR in variable selections. Then we use the machine learning to develop a model, and we expect this kind of machine learning based model can have a better model prediction performance, because this one people usually say machine learning can depict better in linear and nonlinear relationship. And we also finally use the best model we developed to estimate the NO2 variability for almost for the past 20 years. And the output from our model, we will earn a grid-based map. And for each grid size, for each 50 times 50 square meter areas, we will have one NO2 predictions level from our model. And this one is daily with daily resolutions. Okay. So first, let me introduce the database we use in our model. So we collect the air pollution measurements from the Taiwan EPA. So we have around 76 mining stations. Our study years are around from 2000 to 2018. So we have data for the past 19 years. So we use a daily average resolution. We use a daily resolution database, the data from the Taiwan EPA. So totally, we have a big database for air pollution measurements. We have around 0.5 million observations from the Taiwan EPA. This one will be used as dependent variables for the model development. So we also collect the co-pollutants from the Taiwan EPA as the predicted variables. So we also have information like a PM10 and SO2 ozone. And we also include some weather factors like the temperature and the humidity and also wind speed as predicted variables in our model. As for the land use land cover predicted variables, we try to collect different types of land use land cover allocations from several GIS databases. For example, from the digital road network map, we can know the spatial distribution of local road, major road, and all types of roads. And we also have the land use land cover distribution from the land use inventory from our governments. So from this database, we can know the information like the pure residential area, different types of residential area. We also know the distribution of the paddy, orchards, farmland, water body, and also different like airport and harbor. So we can have this kind of information from this land use inventory database. And as I mentioned to you, because I want to consider I want to incorporate the culture-specific sources in our model. So I also have a landmark database from private companies. And from this database, we can know the distribution of temples and trust restaurants in the whole island of Taiwan. And we also have the data about the spatial distribution of the industrial park. And we also consider the distribution of the coal-fired power plant in our model. And here, because some studies, they also stated the the roles of vegetation in air quality purifications. So we also use satellite-based measurements to identify the spatial distribution of the vegetation in Taiwan. So here we use NDVI, this kind of a spectrum-based vegetation index to represent the distribution of vegetation in Taiwan. And we also consider some topographic factors like elevation, aspect, and slope. So basically, we just try to extract all types of land use land cover information by using a GIS systems. For example, here, this is the green points over here is the monitoring station, right? So first, we use the GIS to generate different types of buffers, circuit buffers. So here, the size of the circuit buffer used range from 50 meters to 5K meters surrounding by the monitoring stations. So we just try to calculate the density of the number of landmarks within these 14 buffer ranges. So we can earn a very big database for the spatial predictive variables. Total we have earned around 600 predictive variables from these geospatial land use land cover databases. So these 600 predictive variables will be used to develop the air pollution prediction models. Okay, so here's the framework for the whole study. So in the first step, we try to develop some database. We have an air quality database. We also have the GIS, the land use land cover database, right? So in the second step, we try to use the land use regression model to identify the important predictive variables. Then we just apply the selected predictive variables into 3 types of machine learning algorithm, including the neural network, random forest, and the XGBoost. And then we try to conduct some model validations to confirm the model reliabilities. Then we apply the best model we developed to predict the NO2 gradient maps for the main island Taiwan. So in the first step, at the land use regression stages, totally we applied 2 types of land use regression in this study. The first one is a conventional land use regression. So here we use the land use land cover as predictive variables to develop a multilinear regression model for NO2, no problem. But in the second one, I just use the method I introduced to you, the hybrid Kriging land use regression model. So this time, we also have a land use land cover information as predictive variable over here. But we just include 1 more predictive variables, and this one is obtained from the Kriging interpreted pollutants levels. So we include this new predictive variable to see whether combining these 2 approaches could improve the model performance. And land use regression, the computer land use regression will select the important predictors variables. Hybrid Kriging land use regression will also select the important predictive variables. So we also want to see whether this one or this one have a better performance in model development. And here we use a stepwise variable selection procedure in multiple linear regressions. We use a p-value smaller than 0.5 and smaller than 0.3 for variables entered and removals respectively. And we also consider the model collinearity issues. So we use a VIF smaller than 3 as a criterion. And as I mentioned to you, we also consider the direction between the dependent variables and the predicted variables. So only the variables with the right direction will be selected as the important variables. And let's move to the machine learning steps. So here I apply 3 types of machine learning algorithm: DNN, random forest, and XGBoost. Random forest and the XGBoost, both of them are decision-based algorithms. So basically, in this kind of algorithm, they just try to divide several and many small explainers, then integrate all of the prediction from this small explainers to obtain the final predictions for the model. And the DNN just like the very typical neural network approaches. So we also give a try for the deep neural network to see whether this one can predict NO2 variation good in Taiwan. Okay. So basically, any models were developed in our study. So the first one is we have a LUR variable selected from LUR. We also have variable selected from hybrid LUR. And we use this variable to develop the linear regression for itself. And we will also use this selected variable coupled with different type of machine learning algorithms. So totally we earned added models developed in these studies. So we use several ways to confirm the model reliability. For example, in the first step, we try to randomly divide the data into two categories. The first one is testing data set with 80% of the data, 20% of the data as a validation data set. And we also try to conduct a tenfold cross validation to see to check the model reliability. And we also try to lift the data from 2017 and from 2018 as external data to confirm the model reliabilities, and also try to calculate the R-squared by season and by 6 major cities to see whether our model have some overfitting issues in different seasons or different cities. And we use the R-squared and adjusted R-squared to represent the predictive ability of the model. We use MSE, MAE, and RMSE to identify the errors of the model. So this picture shows the trend, the temporal trend of the measurements of NO2 in the past 20 years. So basically you can see there's a decreasing trend in the past 20 years. And the average number of NO2 is around 17.7. So if you compare with the standard from the Taiwan EPA, the standard is 30 ppb. So basically we can see this one is good. I mean, Taiwan EPA really have a good work in controlling the NO2 emissions. But if you check with a new criterion from the WHO, we still have much efforts to do to make this one better. Also, here is also the best plots for the NO2 measurements from different types of mining stations. So no doubt we found that we have higher NO2 levels in traffic stations, and we found the lowest NO2 levels in the national park stations. Okay, so this table will show you the variable selected by the conventional LUR and also selected by the hybrid LUR. So you can see several types of the linear variables were selected in these two models, like the industrial and commercial residential areas, the major road, and also the manufacturing, and also a major road density, temple, and also forest, and also distance to the water bodies. And of course, in the hybrid LUR, one more predictive variables, the collision interpreted NO2 levels was selected in the hybrid models. So this table will show you the model performance of land use regression based machine learning models. So here you can see there's a green square over here. So this is a model R-square from the land use regression, the most conventional approaches. So I want to use this one, the 0.65 as a reference. Then I will compare this reference with the proposed approaches. So here you can see LUR, the R-square 0.65. LUR coupled with DNN, coupled with land use regression, with random forest, and coupled with attributes. There's an increasing trend in the model performance from 0.65 to 0.84. You can see the model looks like much better. So here's a validation for the LUR for the LUR-based machine learning model. Here is a R-square based on when we compare the predictions from the models and with the measurement from 2017 and from 2018. So the main model, the R-square is 0.68 for LUR, and for the rest of the machine learning-based model. And you can see the number between the main model and also for each year of the external data verification, they are very similar. So that indicates we don't have overfitting issues in these models. So let's move to the hybrid based models, coupled with the machine learning algorithms, the results from the model performance about the model development. So this time, the hybrid model compared with the conventional LUR, the R-square is 0.78, much better. And when you couple with the machine learning algorithm, it's much better compared with the previous slides. You can see in the best model, hybrid LUR coupled with attributes, the model performance is around 0.91. Very, very good, they say. So again, here is a table for the model validations. Here is the R-square for the main model, R-square for the data from 2017 and from 2018. Very similar, so no overfitting issues. So this table just show you the NO2 NO2 levels from the measurements and from the predictions by season. So overall, you can see the value between the measurement and the predictions, they are very close. So our model performs very well in prediction NO2. And this time, we just try to certify data by city for the top 6 cities in Taiwan. Again, the model predictions shows a very similar values with observations. And finally, this one just shows you the predictions and the observations for the past 20 years. They are almost overlapped together. And here's the mean values for predictions and the observations, very, very close. So that indicates our model performed very well and no overfitting issues. So finally, we just use this, the best model, the hybrid prediction at UR, coupled with attributes to predict the NO2 variation in Taiwan. So this map shows the average values from 2000 to 2016. So we can see the spatial distribution of NO2. We have higher levels in the major cities and lower levels in the eastern part and also in the mountainous areas. And from 2000 to 2016, there's you can see the red areas indicates the higher potent areas, but you can see the potent shows a different trend during the study period. And here I just want to show you the narrative of NO2. Again, from spring, summer, fall to winter, we can find there's a higher potent levels in the cooler season like the spring and winter, maybe due to the atmospheric conditions and also the dispersion issues. So finally, is my conclusion. So we propose land use regression-based machine learning models for NO2 predictions for the mainland of Taiwan. We found that this kind of machine learning-based model will predict the NO2 variations in Taiwan, and the overall model performance can achieve can explain around 90% of NO2 variation in Taiwan. So we will apply this kind of air pollution prediction to we'll work together with the other professor to see how NO2 will affect the health effect in Taiwan. And that's it. So I want to show my appreciation to NHI again. Thanks for NHI's long-term support on me. And that's it. Thank you very much for your listening.
Okay, thank you for Professor Wu's wonderful presentations. Any questions for Professor Wu? I don't see anyone raise any question at this moment. Okay, I have my first question for Professor Wu is you choose significant factors based on like land use regressions, and then apply this factor into machine learning. And I wonder if you didn't do this step, just put everything into your machine learning. Which one will be better?
No doubt. If you don't do the variable selection procedures, I mean the full predictive variables model will perform better than my results.
So what's the importance of this measure to select variable?
Yeah, I think
because I find your best model, the major rod was not included in your as a significant factor in your machine learning model. Say for NO2, I would like to say like automobile emissions. So traffic density is very important.
Yeah.
Say I don't see why you don't include this in this variable in your model. And so I think that's my second question.
Okay, so let me confirm with you, Professor Tsai again. So this is a table. This table shows the selected variables by both land use regression and also the hybrid land use regression models. So that indicates we use these selected variables and coupled with the machine learning to finalize the prediction model in our study. So you can see this is our best model. We use a hybrid. Our best model is a hybrid coupled with the machine learning, right?
Yes.
So here you can see in the hybrid model, we also, this one, the major rod density density within the 15-meter buffer ranges was also selected as an important predictive variables in the model. So we indeed have the road distributions in our model. Yeah. And the second, about your first questions, my idea, I mean, more and more people apply the machine learning algorithm in different study fields. But one of the core issues for the applications of machine learning algorithms is is overfitting, let's say. You can, of course, for example, in my case, I have a spatial predictive variables with around 600 predictive variables in the database. I can just simply import all of these 600 predictive variables into the machine learning to develop the predictive model, no doubt. But the question will be, you use 600 predictive variables. So the first question will be, is it necessary to consider all of these 600 predictive variables? This is the first question. The second question will be, what is the coefficient estimate for each predictive variables in your model? Because as I know, we don't really know the real correlations between every predictive variables with the air pollutions from the machine learning model. That in case, even though I import the major road density within 15 buffer ranges as an important predictive variables in the machine learning model, after the process of machine learning, they don't really show you this one is positive or negative correlated with your air pollutions. So that in case people want to know, based on our knowledge, only the important predictive variables should be used in the model. Only the variables which make sense should be used in the model. So in the case, I use all of the 600 predictive variables, but finally I found out road showed a negative association with an NO2. So this one makes no sense, right? But after you use the machine learning, sometimes due to a very complicated computation process in the machine learning algorithms, sometimes you might find out the major road is I imported this one in my model, but this one showed a negative association with the NO2. But you use this kind of association to build a model. That makes no sense. So my idea, we just try to filter out only variables with right directions and also achieve the statistical significance levels should be used for developing the machine learning based model.
Okay, I got one question from our audience. Hongji,
okay.
How about the islands of the nation, such as Penghu, Jinmen, and Three Islands?
Yeah, let's go back to this slide. Actually, I also have some conversation with Professor Wang Zuli in the past. So I know, of course, we have not only from in Taiwan, we not only live in the main island, but we also have people living in the islet like Penghu, Jinmen, and the Lüdao. But basically, the first challenge is to develop the air pollution prediction model for the islet. The first challenge will be the number of the monitoring stations on the islets. As I know, we have only 3 monitoring stations for these 3 islets. That indicates 1 monitoring stations for 1 islet. So in this case, the second challenge will be, basically, we must agree with that the industrial style between the main island of Taiwan and the islet should be totally different. That indicates the emission characteristics will be totally different between the main island of Taiwan and also the islets. So in this case, I suppose in the case that we want to develop a model for this Penghu, Jinmen, and the Lüdao, we should do it separately. We should develop a model for the isolate. We should do it separately. But the first challenge is only 3 monitoring stations, only data from 3 monitoring stations. So this is a big challenge when you develop a model. You say that I will use only data from 3 points of data, so 3 points of monitoring stations. And the second challenge is, in my approach, I basically use the lane cover information as predictive variables to develop my model, right? Let's say for most of the database we use here, we have found the lane inventory, like the digital neural network, no problem. We have the data for both the main island and also for the Penghu, Jinmen, and the other islet, no problem. But for some information like the landmark Actually, this one I purchased this. I just buy this one from private companies. So I'm not pretty sure where they can have provided data for the isolates. But let's say in the case we have the data from, we have the measurements, we have more measurement from the isolate, and we also have the geospatial data for the isolate. Of course, we can do it. Yeah.
Okay. I think time is up.
Okay.
It's perfect time, I think.
Perfect.
Thanks very much for Professor Wu's wonderful presentation. Thank you.
Thank you, Professor Tsai. Thank you, Professor Hong.
Professor Hong. So let's call it our session instead. Okay.
Okay.
Thank you.
Okay. Thanks for Professor Guo Yuliang and Dr. Wu Zhida wonderful informative sharing. And thank you for Dr. Hong and Professor Tsai's perfect introduction. 谢谢郭阳教授还有吴志达老师为我们带来这么精彩的一个演讲哦，并再次感谢洪副院长还有蔡特命教授的一个介绍跟讨论哦。Okay, let's take a short break right now. The next session will start in 20 minutes at 13:10. And thank you. 接下来我们就请各位稍作休息一下，下一个议程将于20分钟后，下午3点10分开始哦，谢谢大家。 time flies. And now for the final keynote speech. Speaker is Professor Sakika Hojo. We are honored to have Dr. Wang Shuli of NHRI and Dr. Wang Linling of Zhengzhou University serve as our moderator. Now let's welcome Professor Wang and Professor Wang. 时间很快就来到我们本次大会最后一位讲者，Sakika Hojo 教授。我们很荣幸邀请到国务院王淑丽研究员和正修大学黄丽颖老师担任主持人。现在让我们来欢迎两位主持人。
谢谢，谢谢，谢谢各位。继续吗 ？OK， 那我来介绍教授吗？好，那我就由我继续介绍北桃教授哈。Hello everyone online. I'm Linling Huang, come from Taiwan, Kaohsiung Jianshu University. Today, I'm very honored and happy to introduce to you Professor Sachiko Hojo. Professor Hojo received both medical and dental PhDs from Tohoku University. Her specialized are environmental medicine and epidemiology. Over the past 30 years, she has conducted multifaceted epidemiological investigations. She was a member of the research team on sick house syndrome funded by the Ministry of Health, Labor and Welfare, MHLW, and now a member of the MHLW study group on central sensitization syndrome. Professor Hojo, please.
Thank you for generous introduction. I am Sachiko Hojo. I am a 70 years old researcher with 4 grandchildren from Japan. I'm very glad to be here. So, started presentation. It's okay? Recently, the rapid increase in the number of patients with environmental hypersensitivity had become a worldwide problem, and the close relationship with allergic disease had been pointed out. However, its pathogenesis remains unclear. In the past 30 years, I have conducted multifaceted epidemiological investigation, including the preparation of a Japanese translation of international common questionnaires to evaluate environmental hypersensitivity, confirmation of its reliability and validity, and setting of Japanese unique screening criteria. I have also been collaborating on a study with Dr. Linling Huang in Taiwan since 2008. Today, I'd like to talk to you about environmental hypersensitivity as indicated in this slide. In 1997, I started a study on sick house syndrome. During the survey on SHS, I found that SHS often progressed to multiple chemical hypersensitivity unless the living environment was improved at the early stage. So I initiated a study on the relationship between SHS and MCS. As I continued the studies, I found that many patients with SHS and MCS also showed hypersensitivity reaction to electromagnetic fields, such as personal computer and mobile phone. Then I started a study on EHS in 2008. I learned that health disorders such such as SHS, MCS, and EHS are known as environmental hypersensitivity, environmental intolerance, or environmental illness. Moreover, I learned that many environmental hypersensitivity in early childhood also develop due to behavioral disorder such as autism and attention deficit hyperreactivity disorder. Therefore, recently, prevention of the onset of environmental hypersensitivity has become a major social issue worldwide. In order to analyze the onset mechanism of environmental hypersensitivity and study prevention measures, it is necessary to exchange information and collaborate internationally with researchers in a wide range of research fields. So in Japan, we have established 3 research groups as shown in this slide. Our research group includes researchers from a wide range of research fields, such as epidemiology, allergy, environmental medicine, public health, architecture, biology, chemistry, physics, environmental engineering, and environmental society. I am the representative of these 3 research groups. Here is a picture of the main member of our research group. Dr. Lin Fan and I are also here. Our research groups are always jointly working as follows. 1. Daily information exchanged by email. 2. Regular meetings. 3. Symposium and lectures for citizens. Environmental hypersensitivity is a health disorder characterized by a variety of systemic symptoms, as indication in this slide. It is closely related to allergic disease. However, the pathophysiology, such as its onset mechanism, has not been elucidated yet. Typical environmental hypersensitivity, sick house syndrome, SHS, multiple chemical sensitivity, MCS, electromagnetic hypersensitivity, EHS. From now, I will briefly talk about the latest finding on these syndromes. Modern people spend more than 90% of their time indoors, and the issue of health risks from indoor air pollutants is important. Following the 2 oil shocks in the 1970s, energy conservation in buildings was promoted in Europe and the US to save on heating and cooling costs. Since the early 1980s, a number of residents from energy-saving buildings in Europe and the US have been experiencing a health problem such as dizziness, nausea, headache, dryness of the mucosal membrane and skin, and respiratory symptoms such as wheezing. These phenomena became a social problem in Europe and the US and were called sick building syndrome. In Japan, since the 1980s, SHS has become a major research project that is being examined by several academic societies and funded by the Ministry of Health, Labor and Welfare's Scientific Research Grant. In 2003, the guidelines for indoor air pollutants have been established. Moreover, the sick house syndrome manual and sick house dictionary were published. In 2012, the Ministry of Education, Culture, Sports, Science and Technology published a document on health hazard due to chemical substances in schools. Thus, Japan has a track record of success in reduction the risk of developing SHS. Next, I will talk about MCS. MCS is a health disorder that presents various symptoms in multiple organs, with ultra trace amount of chemicals that ordinary people do not feel. There is still no universal definition, but the most widely used definition of MCS is the definition of the 1999 consensus. The prevalence of MCS in countries globally ranges from 8% to 33.3%. According to Stayman et al., patients with physician-diagnosed MCS accounted for 12.8% of the U.S. population, and self-reported MCS patients account for 25.9% of the U.S. population. These percentages have tripled and doubled respectively compared to those 10 years ago. In Japan, Uchiyama Murayama applied quiz to Japanese individuals in 2000 and found that 0.74% of individuals exceeded Miller's MCS criteria. However, in 2012, Atma et al. Found that the number of individuals exceeding Miller MCS criteria was 4.4%, an increase of about sixfold. In 2012, we also conducted a survey using quiz and found that 5.8% of individuals exceeded the Hojo's MCS criteria. This result was consistent with the result of Asma et al. And suggests that the number of MCS patients is rapidly increasing in Japan. The 1999 consensus is the most widely used MCS definition. In the 1999 consensus of the Atlanta Conference, sponsored by the National Institute of Health, US, MCS was defined as meeting the following 6 criteria indicated in this slide. The quiz was a questionnaire recommended in the 1999 consensus. So I will talk about quiz from now. The quiz was developed by Miller and Prihoda in the US in 1999 for screening of patients with MCS, evaluation of treatment effect, and performance of epidemiological study on MCS using questionnaire. Quiz is the most widely used clinical screening test and research tool for identifying chemical intolerance. It has been translated into 16 languages: Japan, Taiwan, Australia, Denmark, Finland, Germany, Indonesia, Italy, Spain, Sweden, USA, and Uruguay, with more than 32,000 respondents. This slide shows 50 questions on the 5 subscales of quiz. the Japanese version of quiz, which was translated and confirmed for reliability and validity to establish the unique Japanese screening criteria by Hojo et al. Based on this, Hojo et al. Conducted various epidemiological studies, MCS and SHF, in Japan. The Quiz Taiwan version was translated by Dr. Lin Fang. Now, I will move on to EHS. Hypersensitivity to electromagnetic waves was first discovered in the 1980s. In 1991, Dr. Ray, a U.S. physician, proposed the name electrical hypersensitivity, claiming that microwaves generated by power line and cell phone base station affect the autonomic nervous system and produce health problems closely related to MCS. Subsequently, this study was expanded, and more than 150 researchers from 25 countries participated in the WHO workshop in 2004. In 2005, WHO fact sheet 296, Electromagnetic Field and Public Health, Electromagnetic Hypersensitivity was published. Since then, a number of studies have been conducted, mainly in Europe, and names such as electromagnetic hypersensitivity and idiopathic environmental intolerance have been used. In this symposium, we will use the term electromagnetic hypersensitivity, EHS. However, the scientific elucidation of EHS is behind that of MCS. There is an urgent need to clarify the pathophysiology of EHS. This slide shows the prevalence of EHS, 0.7% to 30.3% in the world. In 2016, Hojo et al. In bioelectromagnetics reported that 3% to 4.8% of individuals were highly suspected of EHS in Japan. This slide shows the estimated prevalence of EHS by Hallberg and Overfeld in 2006. It is predicted that the number of patients with EHS will increase rapidly in developed countries in the future. This slide shows the example of skin lesion observed on the hand of patient with EHS alone and that of patient with EHS and MCS by Belpom et al. In France. The patient with EHS and MCS had more severe skin symptoms than the patient with EHS alone. Next, I'd like to talk about some of my epidemiological research. This slide is a list of my main paper in environmental hypersensitivity using quiz and or EHS question area. There are 3 co-authored papers with Dr. Lin Fang, which are shown in red. In this paper, we reported that we developed the Japanese version of the EHS question area developed by LTT et al. In the UK, confirmed its reliability and validity and set the unique Japanese screening criteria described in this slide. The EHS questionnaire was developed by LTT et al. In the UK in 2007 to assess the health effects of electromagnetic field. This is the Japanese version of the EHS questionnaire, which was modified into a Japanese translation with content suitable for Japanese lifestyle. Added Japanese specific questions such as sleeping hour, chronic disease related questions, and depression scale as shown in red. This slide shows a summary of our study on SHS using quizzing. From the result of our survey on SHS in Japan, the following three conclusions can be drawn. 1. Children, women, and individuals with some allergies are more likely to develop to SHS during new construction or remodeling. 2. Patients with SHS can recover from early detection of indoor air pollutant. 3. If the measures are delayed, it will shift to MCS or EHS. So it is important to detect early and reduce indoor pollutants that are presumed to be the cause of SHS. Next, I would like to introduce our latest paper on MCS. The lifestyle of Japanese people have been changing rapidly over the past decade or so. In order to examine the relationship between changes in Japanese lifestyle and trend in environmental hypersensitivity, we compared quiz score between the old survey 1999 to 2002 and the new survey 2012 to 2015. We report the result in this paper. Next, I will talk to you the main result of this paper. This slide shows the comparison of physician estimated onset factor on MCS between the old and new surveys. In the new survey, electromagnetic field, perfume, clothes, cosmetic, softener, and chemicals in the medical treatment increased, resulting in highly diversified causes. This slide shows the result of comparing the quiz score of the MCS patient and the control between the new and old surveys. In MCS patients, the total score of Q1, Q2, and Q5 increased for 10 years, and the number of avoidance items increased, indicated that the symptom became more serious. On the other hand, in the control group, many ongoing chemical exposure were increased for 10 years. However, the total score of Q1, Q2, and Q3 decreased, suggesting that, as Miller argues, the manifestation of symptom is only masked and the symptom may eventually become apparent. This slide shows the comparison of the allergic disease complication rate of patients with MCS between the old and new surveys by logistic regression analysis. Compared to 10 years ago, MCS patients had 5.3 times higher in allergic rhinitis, 5.2 times higher in bronchial asthma, 3.8 times higher in atopic dermatitis, and 2.6 times in food allergies. Conclusion of this study, compared to 10 years ago, 1. Opportunity for Japanese people to be exposed to chemical substances and electromagnetic waves were increasing. 2. Factors that can cause MCS were diversifying. 3. In the MCS patient group, the score for chemical intolerance and daily life disorder have increased significantly, and the complication rate of allergic disease has also increased sharply, resulting in aggravation. 4. In the control group, the chemical intolerance and symptom score were significantly decreased, although the chemical exposure rate was significantly increased. As Miller argued, the symptoms are only masked, and it's predicted that the symptom will eventually become apparent. Next, I'd like to talk about our epidemiological survey conducted using the quiz and EHS questionnaire together. This slide shows the course of symptom onset in self-reported EHS patients from SHS to MCS to EHS was the most common course, followed by MCS to EHS, EHS only, EHS to MCS. Thus, more than 80% of self-reported EHS patients also had MCS. This slide shows the course of symptoms in a physician-diagnosed MCS patient. The most common was MCS to EHS in 52.7%, followed up MCS alone in 40.9%, and EHS to MCS in 3.6%. Thus, it was found that about 60% of physician-diagnosed MCS patients had EHS. This slide shows the result of quiz symptom score of patients with MCS and EHS combined, those with MCS alone, and those with EHS alone. MCS and EHS combined type scored significantly higher than the single types. This slide shows the result of comparison of quiz score of 5 groups. MCS in red and EHS in blue had significantly higher score than the other 3 groups. Bronchial asthma in green, atopic dermatitis in purple, and control in black. However, there was no significant difference between MCS and EHS. There were also no significant difference among the 3 groups: bronchial asthma, atopic dermatitis, and control. This figure presents the comparison of the score of 9 types of EMFs: computer, electrical applicants, fluorescent lighting, microwave oven, mobile phone, power line, radio television transmitter, telecommunication math, and television related to the onset of symptoms on the EHS questionnaire in 4 groups. The highest score were in the EHS in blue, followed by MCS in red, bronchial asthma in green, and control group in black. All 9 types of score in the EHS group were significantly higher than those in the MCS, bronchial asthma, and control groups. Particularly, the score for telecommunication, math, and mobile phone were high. These results were similar to those of Eltit et al. In the UK. This slide shows the number and percentage of those who exceeded the MCS or EHS criteria. In the control group, there were 5.9%, 4.6%, and 1.2% of those who exceeded the MCS criteria, those who exceeded the EHS criteria, and those who exceeded the MCS and EHS criteria, respectively. It was suggested that those who exceeded these reference values may be patients with MCS, patients with EHS, or patients with MCS and EHS combined. It was also found that the number of patients with bronchial asthma and atopic dermatitis who exceeded the standard value was significantly higher than that of the general population. Now, I will move on to my final message for this presentation. Conclusion 1. 1. Environmental hypersensitivity, like allergic disease, is a health disorder that affects any modern person. 2. In Japan, there are potential patients with environmental hypersensitivity at a rate of 3 to 6%, and there is a possibility that the number will increase in the future. 3. Children and individuals with some allergic disease are more likely to develop environmental hypersensitivity. 4. Patients who develop environmental hypersensitivity in early childhood are more likely to have behavioral disorder. 5. In order to analyze the onset mechanism of environmental hypersensitivity and study preventive measures, it is necessary to exchange information and collaborate internationally with researchers in a wide range of research fields. 6. For collaborative research, the International Common Questionnaire, such as QUIZI, used in many countries, is an effective tool. Conclusion 2. The pathological mechanism of environmental hypersensitivity can be explained by the 3-stage hypothesis indicated in this slide. To prevent environmental hypersensitivity, it is important to identify the environmental factor in the 2nd and 3rd stage early and preventive or reduce them. Finally, I'd like to thank all the researchers who are part of 3 research groups on environmental hypersensitivity in Japan, as indicated in the slide. This is the last slide. With COVID-19 may increase the number of patients with environmental hypersensitivity due to increased opportunity for chemical exposure such as disinfectant exposure and electromagnetic exposure due to increased online work. I am researcher with 4 grandchildren, so I would like to continue my research with you in the spirit of Think Future, Act Now. Thank you for your kind attention. That's all. Thank you.
Thank you so very much to Professor Hojo's wonderful talk. And so let's start the question. We have from audience about the question about any underlying reasons for the observation that early MCS make multiple chemical syndrome over the last 10 years increased ADHD, that's 过动自闭. Could Professor Hojo provide some questions why MCS cause ADHD? Professor Hojo, please.
Thank you for the question. That your question is why MCS onset factor is diversified. It's that question.
Yes. Yes.
So,
autism.
Yeah.
And yeah.
I think there are many. We have many opportunity to chemical. For example, we made many chemicals. We use many chemical. For example, performer or softener and say many chemical we use, and moreover we use the exposure the electromagnetic heat exposure. For example, many IT item develop, so we have many opportunity to exposure by electromagnetic field. So, and with corona, with COVID-19, we use the we had opportunity many opportunity to online meeting on the online work. So and 5G, what they many many electromagnetic field increase. That's why I think
right.
MCS and EHS patient increase. I think.
Yeah, thank you so much for the emphasis of now we use a lot of electronic devices, particularly for the COVID-19. And it's very important, Professor Hojo, that emphasize the electromagnetic hypersensitivity is also very important for well-being.
Thank you.
Thank you. Yeah, and we have also another question about the reason why MCS again MCS is increased so much during the last 10 years. Although we have put a lot of efforts, including Japan, of course. Yeah. So please, Professor Hojo.
What was it?
Yeah, we have been making a lot of efforts during the last 10 years, but the prevalence of MCS still increased a lot.
Yeah.
So, how do you think about the reasons?
So, chemical, but the MCS, we use many chemical, yeah, insecticide or side softener, and in Japan we have a problem in the perfume problem. Okay, many people and some people think the good to smell, but many but say perfume. Dinding, Dr. Dinding, as a 香りのguy, perfume guy.
香害
Do you
对
have
香
in
味的
Taiwan? Yeah, 香りのguy. With perfume problem. Many people use the perfume, very kind of perfume. What say?
Yeah, perfume. Yeah, yes. People use many personal care products like perfume. Yeah.
Personal care product. So, do you have the same problem in Taiwan? No.
Yes. Yes.
Yeah.
Yeah, and so sometimes people clean a lot, but put a lot of personal care products too, and to smell good, but it might not be good for indoor air.
Yeah.
Thank you so much for the reminder.
Yeah.
Yeah, and yeah, this is a very wonderful talks, and we have 2 more questions. And thank you for the audience passionate discussion. And so, do you think because of the COVID-19 pandemic, do you think that multiple chemical syndrome might aggregate the infection or symptom of the disease resulting from COVID-19 infection? Yeah. Yeah, please.
Yeah. What's it? You have a question? So?
Yes. We have audience asking whether the multiple chemical syndrome may aggregate COVID-19, maybe infections or symptoms. Yeah.
So we in Japan we use many in this infect chemical. Many chemical disinfection chemical. We can exposure. So.
Yeah. So.
I think the may increase the MCS. It's okay. No.
Yes, I think the answer is yes, because of the sickness and source of health effects from the MCS, like a fragile, so which might aggregate COVID-19. I think. Yeah. And also the last question here. Would the EHS mediate the chemical component of electronic device? And I am not quite sure the question, but it seems to me that would the chemical and electronic devices interact to when both multiple chemical and electromagnetic exposure exaggerate the hypersensitivity.
Combined chemical exposure and electromagnetic field exposure and combined. So combined patient have a severe symptom. Yeah, and not it's difficult to care. And
Right.
Yeah.
Yeah.
So,
yeah. I think this is very important, and the answer is yes, but it's not so easy to measure, to evaluate, right? Yeah, yeah. Thank you so much. I think this is the last but least talk, because we usually use chemical measurements, but electromagnetic hypersensitivity is there. And Professor Hojo tackled the very difficult measurements and provide us many scientific evidences to care for well-beings. And because we stay indoor quite for a long time, and definitely we must collaborate and to tackle on this important but difficult issue. Yeah. And thank you. I think the time it's about the time, so I hand it over to Dr. Wu Wade to continue this wonderful forum. Thank you.
Thank you.
Okay. Thank you, Dr. Wang. Thanks for Professor Hojo wonderful and interesting talk. And thank you, Professor Wang and Dr. Huang for great introduction and discussion. 谢谢 Hojo 教授为我们带来非常这么精彩的一个演讲啊，并感谢两位主持人王老师跟黄老师的一个介绍哈。The time passed surprised quickly before come to the end of today's conference. We are very delighted to invite Professor Chen Baozhong. He is the chairman of our conference to sum up today's presentation and give us the closing remarks. Welcome, Professor Chen Baozhong. 今天会议的时间过得很快哈，今天的会议即将进入尾声。我们再次很荣幸邀请我们大会主席陈保忠所长来为我们进行一个闭幕的一个致辞。现在就让我们用热烈的欢迎来欢迎陈保忠所长。谢谢。
好，谢谢今天所有的主持人哈，还有这个所有的演讲者了哈，特别在最后面我们的Hojo先生的演讲哈，非常的跟前面的空气污染演讲非常的不一样哈。不过空气污染绝对是一个化学物质，很多的也会有类似的这个健康上面的影响啊。那就像我们的常常很多的过敏性疾病一样啊，其实是有一些雷同，可是又不是很清楚啊。所以今天到今天的最后一个节目啊，我们从早上到现在，其实有关这个空气污染的议题哈，还要持续的努力的哈。特别今天演讲者也不少的提到，上个礼拜WHO 才公布新的 guideline 啊，他的目标当然非常的理想哦。他说现在全球每10个人都会其中有9个会呼吸到这个不干净的空气，只有1/10是干净的。就我们看了一下哈，可能连我们的台湾的东部都变成 都还不是很好，所以呢，值得大家再继续努力的哈。那我想今天才是一个开始的哈。那精准环境医学研讨会呢，我想持续在明年会持续的办理。那当然今天也是公共卫生联合年会的第一天了哈。那第一天就非常的精彩的带入这个在环境中最重要的议题了，所以这个后续呢明天下午1点半又持续在这个所谓环境健康势能，就是说怎么民众了解这个环境的议题的相关的讨论啊，所以欢迎在明天下午，也就是联合年会第2天下午1点半，也是在继续会探讨有关环境健康在民众的势能的提升哈，在现阶段空气污染无法控制的很好之下，在怎么样增加民众的健康势能来保护自己，这也是目前可以立即进行的地方。所以我再一次谢谢所有的主持人、演讲者，还有所有的线上参与的听众啊，老师们、学生让我们今天度过一个非常充裕的这个知识的飨宴哈。那我们可以也学会到很多重要的议题哈。最后呢，明天是我们的台湾的教师节哈，也最后面敬祝这个我们所有的全国的公共卫生的老师哈，老师们教师节快乐啊！虽然现在没有放假，明天还是继续要上班敬祝大家这个教师节愉快哈！特别在这个新冠肺炎疫情之下哈，其实在这个用线上的讨论是一个很好的一个交流的管道了，希望我们可以持续的讨论。再一次谢谢所有的每一位的参与者哈，但我应该今天还是要谢谢我们的威德了哈，他今天负责整天的串场，吴威德博士哈，谢谢他的，还有我们的工作的团队，谢谢所有幕后的协助的同仁哈，再一次谢谢所有人敬祝大家健康平安，谢谢。我们的今天的大会议就到这边结束，谢谢每位，
谢谢，
再见，
拜拜，
谢谢
，Thank you，
Thank
北
you
條先生
Thank you.
，Thank you。
北條先生、ありがとうございました。